but I have it open now.
Okay. Let me. Yeah, this week I forgot to pick up paper earlier. Okay, I started the recording. I forgot to pick up, so I just picked the first one. I saw interesting findings. Next time I'll try. I look a bit more and think was more about which one to pick. But this one was just. I realized yesterday I hadn't picked a paper and just picked whichever one.
Has anyone here read this paper in the past?
I haven't seen it. I mean, I saw it on my Twitter feed and posted here.
Yeah.
So I haven't read it.
It's new, so I don't think so. It's like from very recent. So yeah.
Yes, but
I looked
it
up the
looks
author.
interesting.
They're from UC Berkeley. Grass in there. Yeah.
Also, if people have some idea of some paper to read for next week, put it on the reading group channel or something. I'll probably going to. I'll try to late after the reading group today pick the paper for next week instead of waiting until the last day. But yeah, otherwise I'll probably just look through the previous ones because there's probably some important ones that we haven't read. But today let's just read this one, I guess. Unless we start reading, it seems very not interesting. We could switch to something else. But let's try.
They have code on page 11.
Okay. Okay, let me. Although linear representations of underlying neural networks suggest the fundamental properties remain poorly understood. Striking. Oh, hi. Striking example is the emergence of simple geometric structures in LLM representations. For example, Cameron models are yeah. Also, this one seemed related to the one we saw yesterday. Yesterday, I mean last week.
You mean last week? Okay.
Yeah, that one. And see the scientists is coming for yeah, we know all those things. We show that the statistics of language translation symmetry. The correct probability of 2 months depends only on the time interval between them, and we prove that the latter governs. That would be interesting. It's true. That seems suspicious for being the kind of neat theoretical result that is actually not. Doesn't match reality that people come up with.
Yeah, let's see.
Especially governs the first. This sounds very strong. Maybe it's not as strong, but it sounds very strong to be true.
I would believe. I would believe if there are some ablation studies that support this. Basically, if you, what was it? Co-occurrence, of the probability. So if you like increase the probability of some 1 month, if that would break the geometry, basically.
However, we find that these structures persist even when co-occurrence statistics are strongly perturbed.
Oh.
Doesn't this say the opposite thing?
Moreover, we find that these structures persist even when the co-occurrence statistics. Oh, okay. Huh.
We show that these robust natural emergence of the co-occurrence statistics are collectively controlled by their initial constitution-related variable. Be empirical about the word embedding models, the embedding model. Okay, so they do have a theoretical framework. Okay. I mean, maybe the theoretical framework does say this, or maybe the theoretical framework didn't say this, and they found this thing, and they come with a different theoretical framework that also explained the new thing, the fact that it generalized. So I don't know, but that is only the abstract. Let's see what else it is.
Okay, I'm a bit confused from the abstract. Let's see.
Okay. Also, this seems interesting in that maybe there is some interesting paper here we haven't seen. Also, this geometric structure in neural code, including prisms. I haven't seen loops and continuous one-T manifolds. There's emergence consistent.
Prisms.
We are like organizing principles where the Spartans arise. I mean, some of them, like this one, which is I think probably the counting task one. Did have some theory of why at least the circles happen.
That's exactly what's cited.
We provided such a precision geometry reflects despite which concurrent statistics between balls. This seems like a kind of super vague thing of the kind of. In particular, we have evidence that symmetries in the statistics collectively drive the formation of representational manifolds, allowing us to give detailed mathematical explanation of the following phenomena.
Ooh.
Circles in representation of space for cyclical concepts. Find that concepts that the way was a yes. Represent what the manifest continuous sequences.
We provide such that represents geometry. I wonder how they measure the symmetries. Let's see.
Representations of geometrical locations and historical verbs linearly encode the spatial and temporal coordinates.
If you look in the chat, I have shared the notebook that they use for calculating the co-occurrences. Okay.
Yeah, this thing.
That's the notebook
So
for
if
the
you scroll down,
paper.
you can see how they got the plots.
Oh, nice. I see if at some
So
point
it's
we're
reproducible.
confused by some plot, we can look at this.
Yeah.
Nice.
Yep.
I guess a lot of this will be in the paper.
To test this hypothesis, we first examine the word embeddings models. To proceed, we find that these geometries are less in the simple setting. They have a mathematical theory. Example, when the concurrence probability of two decimal pairs depend only on temporal and spatial distances, this model is potentially left for later representations. The varies by zero its principal components. Yeah, I don't know. This could be very cool if true, but this seems like the kind of theory paper it's very skeptical of that. There is a lot of papers like this that are just wrong, right?
I mean, if they have some math that explicitly predicts it emerging,
that could
and
be
then
nice.
ablations, but they said
treat
ablations. I don't know. Let's see.
I
Yeah.
just treat this kind of paper as if an LLM had written it.
Oh well. Let's see.
We visualize in that it could be true, but I don't trust it until I'm seeing this. Okay, we visualize the top principal components of the word representation for Kali data historical time, and we show the representation vectors gram matrix. What that is. In the top row, we predict both the embedding theory and the gram matrix. I don't know what a gram matrix is, but we can look it up later. Using the parametrical curves driving correlator. Okay.
Gram matrix includes inner product space. Okay.
Okay, so this is theory. This is dual embedded. I mean, the theory says this and this says this, but people already knew that the wall and like the base embeddings are circles, right? There were citing papers saying that. So I don't see this as showing the theory showing any new thing, right? I could also make up a theory that just says they are circles and I guess it's a bit nice if the theory predicts all the phenomena at the same time in some simple mathematical thing, then it makes sense. But in terms of predicting new things, this is just thing we already knew from the, at least the circle one. Maybe this shape thing is more.
Okay, I thought by emerge from the statistics they mean like they do statistics on top of the training data, but here they have like Gemma 2 and you don't have access to the Gemma 2 training data, or do they do that? Do they train models?
I think
That's a lot of math.
sorry.
Amazing.
Word embeddings trained on Wikipedia. The word embeddings are trained. Sorry, I.
Okay.
So LLM interrepresentations. I mean, the Gemma is. I don't think they train Gemma, but yeah, they don't train Gemma.
Okay.
But they did train this world embedding things on. But maybe it already existed, but it's trained on Wikipedia. The Gemma thing is. But yeah, I guess if they did we'll see the statistics, but they probably did it on Wikipedia or something.
They do Fourier geometry, okay. Fourier embedding. Fourier transform.
Oh, did they? I'm not sure, but I'm going to guess they probably use the word embeddings thing, or maybe they fine-tuned Gemma. I don't know. For the concurrence statistics things, they had to figure out some way. Maybe they just did it on the word embeddings. Word to back. Empirical observations, presentation models for linear. Okay. Symmetry. I think expressions predict the representation of geometry data for this. Yeah, but my main question for this thing is it could be cool, but how overfit are those? Basically,
How overfitted?
The analytical expressions are, because they did new.
I see.
Right, it's not like they discover a new thing on the models from the statistics. Right, they already had papers showing these structures, so yeah. Empirical validation that the predicted percentage of studies is present stable. I mean, if you can predict the geometry from the statistics in some way that generalizes to multiple things, that will be interesting. I think that it would have been very compelling if I had used the thing to find some new representation that hasn't found on another paper, like think of some thing where they would predict a different kind of structure and look for it and find it. Empirical validation that the predicted representation structure is present, stable, and interpretable in both word embedded models and data from embedded models. Theoretical validation that predicts how the error in linear coordinated decoding task is with the proof dimension. Empirical validation. Empirical validation that representation manifolds are robust significant presentations of the quantitative and immediate embedded dimension. Yeah, I mean,
Fourier representations everywhere. Fascinating how Fourier transform can be used in so many places. Yeah.
So token concurrences, yeah.
Both the amplitude and the long wavelength mode. Wow. Yeah, I think it's just the gram matrix is just products, right?
Yeah.
Oh yeah. Yeah. That should be just dot products of all the dimensions. Okay, sure. It's used in kernel functions, I see.
So then, symmetry impaired was.
So yeah, they look at the corpus to get the occurrence probability. Ah, okay.
I mean, the whole idea. Think if it's concurrence, so it's basically literally, they are talking about two token co-occurrences, right? That seems. I mean, I feel like this seems the kind of thing that is unlikely to we are just surprising if all of these things are explained by just that, right?
Like if you think about it, if literally any two tokens that have these co-occurrence statistics create these kinds of circular structures, that's kind of interesting, I think, actually.
Yeah, I
Since
expect
that's
you're
very,
going
very
to
general.
find. Expect you're going to find circular things that are not because of two token co-occurrences.
Yeah, but okay. Yeah, I would. I'm not sure if they do this in this paper, but like, I would try many different co-occurrence.
Also,
basically to test your theory, how general it is, basically.
Also, the whole thing, the counting task is can't be about two token co-occurrences because it's about counting how long a sentence is. That's like not at all about tokens, right? That more it's a higher level of abstraction to that.
It approximates the sentence's length, yeah, because tokens are weird. There was the hard-coded approximation.
But I mean that's
quote.
that's not any two token occurrence. In fact, that's not any token occurrence. Is or unless if you think of in terms of correct occurrences, it's like literally all tokens or something, right?
Yeah, I think they're just doing it on their like if you have trillions of tokens in bigger models, that also it's hard to do, I guess. You get combinatorial
I guess
explosion.
you could consider like how tokens it is a thing about how maybe you can find it through the statistics of how tokens co-occur on a sentence before a line break or something, but
yeah, and the line breaking was so complicated and it somehow works. Would be interesting if you could just derive the structures just from the training corpus like this. So maybe
Yeah, so like word-to-vec is like doing center word prediction, right? But it was not clear that it's doing like co-occurrence matrix predicting that distribution. So it seems like a new result in the literature that word2vec is doing like this co-occurrence thing. Like,
I think it's more trying to say if you have co-occurrence statistics like this in the training data, then your model will learn these circular representations.
no, actually, read that sentence. It says, in recent work, Karkada et al. Showed that such models learn to represent the top eigenmodes of a normalized co-occurrence matrix.
Okay, I see here. 2025. Breaking world embedding geometry. Yeah, I haven't read this paper, the other one. Interesting.
What are you talking about?
So like word to
It's
vec,
in
it's an old paper, right?
2-1.
Like from 2013.
Oh yeah, they think they also it's fine that 2020 2013 yeah. Yes.
Yeah, I guess this fact is like it was recently proven.
Hmm,
I didn't know that.
yeah,
Okay,
that I see.
interesting.
Yeah, the thing is the thing that was saying, but we'll see. Yeah, but like I can see if you have word to vec, I can see how everything can be explained, and maybe you can find why you get from 2 token concurrences the circles. But it seems less of like since obvious code you explain it that way. Actual representations in a bigger model that's doing more abstract stuff. But I guess if you see the same circles on the word to vec, maybe it's could be related. I guess I'll keep reading too.
Right, if you plot, that's on the page 7, I think. Yeah, if you plot the co-occurrence statistics, you see some shapes like the learned representations. I see.
Empirically find that nonlinear autoencoders approximately perform PCA. That's interesting. Leading to circular representations. Proving a spring mechanism connecting symmetry representation represented. Used phenomenon well embedded bodies as well as bodies language. Broadening the scope to handling open border condition and two-dimensional lattices. Giving a test material description of representation manifolds. Importantly, identify the collective of the phenomenon. Okay. Let's see with that. Co-occurrence model with symmetry. We aim to describe the representations committed words and phrases that share and underline continuous constants at the time of year, historical dates, or geography. Denote the mission of the semantic continuum. Okay.
Effectively learn lowering spectral decomposition of pairwise co-occurrence statistics. I see. Oh wow.
With a coordinate system.
But why would it learn it? I feel like you could ask one more layer of why, but maybe that's never ending. I don't know.
Sorry, can you?
Well,
Why does it
yeah,
learn
I'm
what?
just like, why in the first place it learns the co-occurrent the eigenmodes of the co-occurrence statistics. Like, you could, I guess, ask infinitely why, but
I
like,
mean, I
yeah.
feel like you can probably not. I think you can. They just bottoms up in something about gradient, some detailed explanation about gradient descent and why this is useful and why the shape of the gradient, energy landscape leads to that model ending in some
So
position or whatever.
yeah, like in that context, I would want like ablating different aspects of gradient descent and see if that's causal, but that's hard with gradient descent because it's such a unified object. Yeah, but I see what you mean. It feels still
Predicting.
okay, but it's interesting because if you just can take this, if you just can take the eigenmode of the occurrence statistics like this, and on the page 7, I think that they show like that the shapes kind of look like the shapes that are learned by the network. So like if you can just derive the representation that's learned in the model just from doing other statistics on the data, that is very deterministic, you could say. That's wow. That's very, very interesting to me because this way you can predict what the model will learn, basically. But maybe it's not as strong as I'm imagining it. I need to read it in
I
more
think
detail.
I think you are maybe like it's not like the patterns that model learns are like the statistics of the thing, right? This yeah, we'll get to that later, I guess. But
I see what you mean, I think. Like, this still doesn't explain line breaking, and so on.
yeah, like I
But I
can
think
see how
it's
this kind of analysis makes sense for like word to back, but it's hard to how you generalize to actual, assume the impedance.
yeah, they're using Fourier analysis. Oh my god. I would.
Yeah. Okay. It states that when the semantic lattice has periodic boundary conditions that principal component is a function. Okay, but isn't this saying in a fancy way that you are going to see the sinusoid, the Fourier structures that we have seen if you have something that's periodic that is like already what we have observed.
Yeah, I think the difference here is kinda, if I get it correctly, that you get the same or similar structure just from the training data without looking at the trained model, basically. And you see the similar kind of structure by just looking at the training corpus, basically. And that somehow corresponds to the structure learned by the model. So maybe there's some kind of equivalence between you doing this kind of more deterministic analysis and the model doing gradient descent, basically, for this concrete phenomenon. I guess that's how I see it.
But
Huh.
well, I'm not sure this analysis is not just overfitting with math to the things that other papers have already found, because
Like, I think the other papers, they never looked at just the training corpus, right? Or did
let's
they?
say
Wait, there was there
my question is more how. Okay, so you have the
oh yeah.
modular multiplication or modular addition. I can say I can look at that and say, okay, so modular multiplication is also a cyclic thing, so it's probably going to have this Fourier thing. Someone can make a very massive thing about how things that are periodic will have this Fourier structure, but with a lot more mass. Did they add something? You know what I mean?
Like,
It's
yeah,
not.
I see what you mean.
It could be that they added something, but I feel like I don't understand the math, all of this math yet. So this is just not saying the
Yeah.
thing that empirically found by that the periodic thing seems to generalize to other thing, or like the kind of thing that like let's say the universality paper. Like maybe like with the other universality paper was right and the models just learn this kind of structure to do and for group composition or whatever, and then it turns out I don't know. I guess I'll keep reading before having very strong takes on the paper, but I think I don't understand it yet anyway.
Like, if this math predicts the structure learned by the models, basically, if just math looking at if math looking at the training corpus learns the math that some other math learns, that's interesting correspondence.
I just
But
have an
like,
instinct of I see a paper with a lot of math, and I feel like you can be tempted that like this tempted to be like, yeah, it's probably very interesting and true or whatever. And like often they are not. So I, you know,
Is there a plot comparing calendar mounts, historical mounts, PCX? I wanna see a plot comparing like
anyway, I
the
go back to
predictive
the main
structure.
with the main thing. Okay, based on the we were learning feature modifier concept with the statistics based for next this choice, but I that are. Okay, so this is more interesting that so they take this proposition 1 for the 4-year thing and then use it for the month thing, and that seems like it's more interesting if that generalizes in that way. It's more like I would want to see if this is actually useful for something.
Yeah, theoretical. That's what I wanted to see. That's the figure
No,
two.
and then they're still doing stuff on world embeddings, and I haven't seen stuff
This
that
is
tells
interesting.
me that this doesn't just work for simple embeddings, and this kind of method just doesn't work for bigger models. But I
Yeah, I
guess
see what
this
you mean.
could be something where maybe you can learn something. The fact that it learns this on dual embeddings is probably maybe generalizable for the same reasons to bigger models. Oh, but wait, I should briefly check that the recording is working all that. Yeah, okay, it works.
Looks working to me. Yeah, this is the exact plot. Like if you can just look at the statistics of the training data like this and get the same shape basically in some margin of error. That's fascinating.
Okay, this is nice. Predictive variety to novel predictions or theory. Projected are two principal components, one embeddings. That's more the kind of thing that the kind of evidence that convinces me a bit that it might be. I'm so tempted to just you could dump the paper into Cloud and ask what they think about the paper.
That's the option. Why can't I? Lassier curves. Like what I find interesting here is that they take Lassier curve. That they introduce or use a lot of like math stuff that frame. I'm a fan of framing the empirical results in terms of math like this. Because when you do
like
that,
it's overdoing it. It's trying to state a very simple property of the data that the model learns, and like, it's just like not an interpretation, but it's what I'm trying to show is like quite simple.
I guess maybe I feel like there's never an overdoing of math, but I think you could write this paper in a simpler way probably, because the math is extremely dense. But like I feel like the more math you use to frame it in, the more in a way you unlock from pure math, like because you have so many different results in the various math fields. So if you do this framing, you get a lot of clues for free.
The more math you use, the more room is for you to be just wrong in a way that's hard for people to figure out because there is a lot of work to read the math. So I want if a paper uses a lot of math to actually require that amount of math, because otherwise it's just making more work for the people reading the paper to figure out what is going on, right?
Yeah, definitely. If there's an error, then then it's much harder to find the error. And there's definitely like a lot of papers that are like making grand claims and like putting it in the frame of a lot of complex math, but when you look into it, you find out that it's BS, which that happened on a paper I looked at 2 days ago, I think. Yeah. So that was like, yeah, whatever. Yeah, it was like AGI cannot do. I mean, LLMs cannot do word models. They are not AGI, etc. And like the
I mean,
in the title
those
and in the
ones-
paper, it was completely something else. But whatever, that's a
I mean,
separate
those
rant.
ones used to try to frame it because they get viral on Twitter by making
Yeah.
sensationalized crimes.
That's why we looked at it. It was super viral, but wrong, completely wrong. Anyway.
I think being viral on that kind of paper being viral on Twitter is actually very anti-correlated with it being good.
Yeah, I see. Like-
But anyway,
good pure math, I think, makes very good stuff, but it has to be correct. It doesn't have to. It has to, I don't know, not be ideologically motivated, for instance, which increases
I think
probability
this
of
one is
error.
nice if it's if they seem to have if I understand it correctly, they seem to have shown predicted some shapes that they hadn't seen before, which is nice if that's true.
Like, you could use. I wonder how general this is. How much you can generalize this. I had like, yeah, a lot. I might have to. I might look into this more. Like, I would have to spend more time of like
yeah, maybe
plugging
this is not
concrete numbers in the math.
maybe
to
this
see
is
it all more.
not the kind of paper that is easy to read on the reading group. At least was not the best one to pick, but I will try. Yeah, I
Yeah.
feel like when the papers are very math dense, it's very hard to figure out on these reading groups. And I should probably pick more of the time more papers that are also people have different amounts of knowledge about math and all that. I think it's better to pick papers that are more showing the results of experiments, and we can talk about the results of experiments and what they might mean or whatever.
That also, yes.
But
I like
anyway,
it though. Though I yeah, like I will have to spend more hours on this, I think.
Yeah.
Which I might do actually. Like that's actually some like I want Mech Interp results to be framed in pure math, and because if you do that, you just unlock correspondences to results from other applied math fields and from other pure math fields, basically.
Yeah. You know, this
And
nice is just
yeah,
very easy to do wrong. Not only
yeah,
this is not only
definitely.
Mech, this happens all the time in machine learning. There is a whole thing of people making all kind of nice sounding theoretical papers about machine learning that then they are just not true or
Yeah.
nobody cares about because they don't
That is
they
true,
make
yeah.
some simplifying assumption that is not true or something.
That is true. Yeah. Yeah. Like yeah. At the same time, if your mathematical framework exactly predicts the empirical data, just like the empirical stuff, like the empirical results, that's good. So like you can make extremely concrete mathematical framework, which in this context you just take the months or years, whatever. But and then you can just go and generalize. Go ahead.
Could the reason why the framework didn't match exactly what wanted to happen could it be not like due to like maybe how long, like maybe like before with less training it maybe fits the theory less, so maybe after like an infinite amount of training it turns into the theory, so it could be
In
like
this
similar
paper
to
it seems to match, at least for in the figure 2, like theoretical prediction, like if you look at those it aligns.
Yeah,
but it's fuzzy.
And also to notice this is for word embeddings. They didn't.
Yeah.
It's weird how it's only for word embeddings, but the non-word embeddings don't match as much.
Where is graph for non-word element? Is there a graph?
Or I guess there is a graph here that.
Yeah, the
kind of,
calendar
but I
month,
think-
they show how like the hidden activations are
Agree what?
clearly not matching.
Calendar months.
Calendar months. Theory, word. Oh, okay, I see. Oh,
But that's an interesting case. It seems like
interesting.
it's matches a bit more on the Yemma than on the word embeddings.
So why does it fail in the
Wow.
activations but not the word embeddings?
I think you're right that it's
Huh.
because the activations have more training and yeah, but I'm not sure.
Hmm.
Or I think it's possible that things like that. Gem actually has seen a lot of things more about months. Like it has tasks that use months. It has other things that use months, and there's probably
Hmm.
there is some other things that are going here that are just not co-occurrence in some text, right?
Hmm.
Like the word embeddings you can think of, they are mostly tracking things like how often is there are lists that are like March, the months in order or things like that, and you can probably get the thing from that. But GMAT can be getting this structure can be being reinforced by more abstract patterns, which in the end is more like it's more apart from that, it's just more data, more training data, I guess.
That makes sense.
But I
Like
think
there's more
you'll
than just
have more.
co-occurrence statistics.
I expect you'll have more efficiency on learning this kind of thing on the Gemma than on word embeddings. Or the embeddings thing, that word to vec state thing with you just train it directly
Yeah.
on something or something. You train a big model, you should find more like you should be more efficient to learn some kind of even the simple structure of the how the months are structured or whatever based on that.
Oh, okay. Yeah, I see. Yeah. So the symmetry, by symmetry here they mean the fact that the distances are the same. Right. I think.
I need to drop in a few minutes for another call. So, like, but can you just summarize like paper in like 5 minutes? I mean, like what
Okay.
your key takeaways are?
I'm not that sure I understand the paper yet, to be honest.
Yeah, maybe I'll take a look at it
Yeah.
after.
Yeah, I think we can, since we are going to we can quickly go skim through the rest
Mm.
and see something.
It's nice that they use symmetry this way. I wonder how much this relates to physics, because there's so much symmetries in physics as well. And do they also... Something I'm asking myself sometimes is like if Mech Interp is just rediscovering different tools that different
It could have been
fields use.
rediscovering the entire time, maybe.
Word embedding models, space in elementary functions. Cyclic time exhibits circular geometry. Absolute time is represented as one-dimensional manifolds, and geometrical equation can be decoded by linear probes. We have shown that this operator universal behavior emerges for unifying principle. Pairs of words that correspond to similar time or space occur more frequently in test. I think this is true on the word to vec thing. This is not just true on the. Okay, it's true that this can emerge from that. I expect on the actual language models it depends on more thing. This effect is very much collective since many words are seasonal here with us. Consequently, the representation geometry is remarkably robust to local perturbation and statistics. Which, I mean, to this kind of local perturbation test, I will have to see like how does that not show that their other thing is wrong, but yeah. Intriguing question is sure was programmation neuroscience is wet. In this pet was nothing that great sense when going to special.
You just have to perturb harder. So that it breaks.
Oh, that's almost. Limitations. Theories set the word of yeah. Remarkably demonstrated those cartoons more expressive members. However, had the ability to adapt to context. For example, please measure resolve. A very stative sample containing may probability station with context, but may be become increasingly sequence the propagate through the overpass. Boolean theory expression framework will be tested. In this work, we are considering the fact that words can expressed by continuous attributes. Testing previous one. Yeah. So I guess it's mostly the thing is they take the paper. They have these results that they have the results that there are these structures on the tech or that there are these that they think that you can predict that models will learn certain structures from the geometry of the CKD left. Yeah, the geometry of the for the statistics of the text, and they have this theory of how you learn that. Okay, so my problem with this is I feel like in the word2vec thing, isn't the co-currency of words the main thing that is like there, right? On the wedding stuff. So it's like you are saying that isn't it saying something about the training data causes this in some sense? Or I guess yeah, you have this nice math thing, but it's like wouldn't the equivalent math thing for the how much is this adding something? I'm still not sure. It seems possible to me that this is basically not adding much.
Like,
but
it feels like it's like this we can derive the structure of the model, and it's just from looking at the data on the training data. But why? Like you could derive different structures from the training data, and why does the model not learn the other structures? I guess that's another aspect as well.
Also,
why does it learn this one, not the other ones?
Oh, they can ask on the chat. So, what if you ask the model to describe January plus February divided by 2? I'm not sure I understand the question exactly. Oh, you mean for the
distance between? Yeah, like
yeah, I mean,
yeah,
I
the
think
distance between them.
Yeah,
Okay.
I mean, I think you could easily train a model that was learned like that to add months. By default, it doesn't necessarily do that, right? But it could learn to do the kind of modular multiplication thing modularization thing that it does on the other thing. And by default, I think what happens if you train it at one is just it's what happens when you train a model in modular addition, because it's not like January means January.
Like the at least most I see the intuition as like the January's relationship to February should be statistically similar to June's relationship to
I don't
July.
think if you just do a model that has not been trained on doing any kind of math with the months, if you just do January plus February, it actually adds them and you get the corresponding month, because that requires an extra thing that the models that learn to do the kind of for example, the modular algorithm mechanism, or the one in the other paper, the models use trigonometry to do arithmetic, is that they have the same structure in the embeddings, but they have an extra thing on the attention and the MLP, that even if the model has it for the numbers, right, and they are the same shape, they are not necessarily the same shape on the same dimensions, right? So you have a thing that if you put two numbers between say a adding sign, it's not by default going to add them in the nice way. But I will guess that if you try to train the months, like the model, to do this kind of addition with months, it's going to be much easier, and it's going to reuse the modular addition. I mean, I'm curious what actual current models will do, but I probably have seen that a lot of. That's probably much more complicated story. But if I imagine like some small models learning to predict, very small models learning to predict this and learning some simple stuff, and then trying to do math with the thing, I don't think necessarily will work. Like if you take GPT-2 and you ask it to what's January plus March, well, maybe GPT-2 will, I don't know what it does. Maybe we
I
should
think it
just
would align.
ask this question, January
Like the-
plus March divided by 2 to GPT-2 or something.
I think the issue with January plus March divided by 2 is like there's more to January and March than just the distance between them in time, basically. So you're also doing algebra with so much other semantic stuff.
I mean, I feel like there's some objection to the whole paper, the whole idea of the paper, right?
Yeah, in a way. I think that's why that's why it's fuzzy in the graphs, like that. It's you don't get a completely perfect curve, and maybe if you train even in the limit, somehow you will still not get a perfect correspondence in a way, like because it's just fuzzy. There's more to than just this distance between the different months of the year. So like a theory, some other theory, like maybe like there's a theory that's like this is what predicts part of the unexplained difference between the theoretical predictions and the empirical observations, basically.
Because there's a foundation. Because isn't proposition 1 just saying that if you have a periodic thing, is going to learn some Fourier structure with some some, like, is it saying anything that we haven't just observed for the existing papers?
Like, I think it's more like we have these empirical results. Let's try that correspond to some math. Let's try to find the same kind of math in the just by looking at the trained data without using deep learning. I think that's how one should think about it, and then see those correspondence. Approximate
Yeah, but
correspondence.
I don't think this is contentless from the training data. They have a prediction that if they hadn't seen the transformer, the example, right?
Yeah.
Because this doesn't say anything about for this training rate and reasons. We show we showed the other thing. Is it like I'm missing something, or they are just starting with assuming the Fourier structure and then having something about how you get the Fourier structure, different Fourier structure for different data, right? I'm not sure if I'm explaining the thing correctly. Maybe I just misunderstanding.
Like, given empirical data, given empirical structures in the models, here's how we mathematize them in them, and here's how we find the
I'm
same.
not sure if that's what they are doing. That's the thing I'm saying. Then the PC. Okay, maybe this. Okay, let me assume the absorption holds so we can see. Assume the. I feel like I don't. I will need to spend a lot of time understanding this to figure it out. Is the. Maybe I need to ask Claude to read it. This is also I think the.
Assign each month a coordinate on a circle. Like, you have to start with assigning each month a coordinate on a circle in this proposition.
I mean, but doesn't that is assuming the thing that you already know, that you see that the months are a circle and you say, if you're assuming each month has a position a circle, then right?
Huh. Kinda. But you have assumption 3.1, which is the translation symmetry. So you assume that 2 months depend only on how apart they are in the calendar. Which is, yeah, it's a simplifying assumption. Like, ignore a resistance kind of assumption.
Okay, but can you... Is this a fancy... Wait, is that just a fancier way of... how do you get the circle? It's my question. From the distance. And is it different from the Westwood net thing when they just say if you want to... The physics thing, where if you want to have these points and be separate, the nice ways to put them on a circle?
Let's see. Under the symmetry, the normalized co-occurrence matrix restricted to the months is circle length. Every row is a shifted copy of the previous one. I think that you get the prediction by taking the occurrence matrix, basically. Since every row is a shifted copy of the previous one. Which makes the eigenvectors sines and cosines. But like you have this assumption, like it feels a bit circular result when I'm thinking about it. You assume that the 12 months have a natural ordering. And that the occurrence probability only depends on the calendar distance. So they assume it, they don't derive it. Okay.
Also, I think I was asking Claude, and I think that I saw something interesting that I not understand better the thing they are saying here, which is the money was association or geographical. Yeah. Okay. So this is meaning the thing is this. I think that the thing they mean here, I was not realizing, is that their take on why, which seems to be a actual counter evidence to their thing, but their thing of why, even if you perturb the even you perturb the even if you perturb the statistics, it's you still see the same representation, which seems like it should mean that it's not actually depending on the statistics, because the result is thing and true is that there is other words that are seasonal or geographically, that you have the concurrence of January with winter related things or whatever, and there's the concurrence of July with summer related things, so you still learn the same structure, and if you remove change the statistics of how often act literally January is near to literally February or whatever. At that point, it feels like
Okay, that's very weird.
you don't. They are not. They're saying you can't actually figure. It seems like you can't actually figure out just for statistics on the data. They're just saying it's learning it from the statistics somehow. Because I mean, it has to, because in some sense, but I feel like at that point you're just saying it's learning from the structure of the data, which is kind of obvious in some sense. But I guess
like from
maybe
Sky
there is
Hurricane
some
Easter Halloween.
interesting thing about why. Maybe there must be some interesting thing about how from the fact that the data does have this structure, because months does have this cyclical structure in a lot of ways, right? Can we predict that they are going to be represented in some way? And maybe they have some interesting math about that, but what I'm not sure is how much this interesting math is some novel prediction, and how much this interesting math is some kind of overfit thing where they know the that the months are represented in circles, and they found a thing that gives circles for that, and the other structure for the other thing, and it happens to match because maybe there is some true thing that's vaguely related or have some vaguely related math. I don't know.
I see. Yeah, the ablation is kind of weird. I guess like they just delete co-occurrence, so they keep January on its own, and the surrounding context is enough. So skiing and winter sky, flowers, spring is related, and that's enough to interpolate to the months, I guess. Consider English Wikipedia. Okay. Okay, you just look at the highly seasonal words, and those are enough to reconstruct the month for the ring. Huh. Interesting.
So does assumption 3.1 make sense to you guys? I think that's the assumption on the training distribution. I mean, the training data.
So let me go to attention at 3.1. Attention is some. So wait, is this the probability? So this is the co-occurrence probability. The co-occurrence words depend only on the distance in the semantic continuum. Okay, but they check that if you change the co-occurrence probability of the months, you say had the same geometry, right? I'm talking about, for example, we have shown that this apparent universal behavior emerges for this. Learn your perceptual reverse to local perturbation to the statistics. So if you local perturbation statistics means they understand they change the co-occurrency. So that seems like assumption 3.1 doesn't actually have to be true, and which
Like,
kind of weird to me.
Like when they do it's in some figure when they do the ablation. What's the figure?
It's also we can see on the thing.
Yeah, if you look at figure 4 on page 7, you just ablate all the months, but you still get a similar shape from just looking at winter sky, flowers, hurricane, and you get a similar co-occurrence matrix just from that. So basically, you get the same shapes by looking at the seasonal words, which makes sense to me because the co-occurrence statistics of these seasonal words should be the same, like the co-occurrence statistics of the months themselves, because they are mentioned with the months approximately. So that result makes sense to me, actually. If I understand it correctly.
Yeah.
Which is interesting. But it, yeah, like, makes sense, I think. Under the co-occurrence frame, like any words that have these co-occurrence statistics should form this structure, basically. And these seasonal words should, I think, have the same co-occurrence statistics like the months of the year. Yeah. I'm gonna try to look through more examples.
Yeah, I think people are living. I feel like I don't know how much. Maybe we should let it not. Yeah.
Yeah, so the
But
math only
there's-
works for like distributions that satisfy assumption 3.1. So that's like their theory.
Yeah, and I think they already said this doesn't really tell us necessarily that much about the actual transformers. It seems hard to see how you go from this to the thing. I feel like
Yeah.
the the other explanation for the Gershwin paper for the curves, how they are just the nice way of packing the efficient way of packing points in some space, seems like it's also
like they
I
do
confuse how much
assume.
that is equivalent.
Yeah, like they do assume that the co-occurrence probability of any two words depend only on their distance.
Yeah.
In the semantic continuum. From symmetry, you get these geometric shapes. So, like, circles have this translational symmetry. Oh yeah, okay. Yeah, they just look at the you just have to have the translational symmetry assumption.
Yeah.
Without that, you don't have this whole framework working. And from the translational symmetry, you derive the Fourier stuff. And the geometry. Right.
So I don't know how this can be extended to like other models because the assumption is strong. Yeah.
If you don't have translation translational symmetry, then maybe you can generalize translational symmetry and use some other symmetries and somehow also derive some shapes using similar method. Like, it would be interesting, like, in physics, generally, you can derive, like, if I get it correctly, like, from symmetries, you can basically derive almost everything. It's whatever. It's like depends, but like I like this whole frame of assume symmetry, derive a lot of structure. This seems to be very physics built in this sense.
Yeah, right. Yeah. That's interesting.
Which is great, I think. And
Yeah.
even like in physics, we just assume symmetries because empirically we found symmetries, and then symmetry is related to conservation of every symmetry has a corresponding conservation law.
Yeah, right.
So
Because
I wonder
saying
if here, like, if the shapes are kind of a conservation law. I don't know if that's.
Yeah, because proving
I know
that
the Noether's theorem. Go ahead.
proving
Go
that,
ahead.
let's say, the global minimum of like the loss function for word to vec has to have this symmetry is much harder to prove than just assuming like some symmetry structure and then showing this part. It's much easier, I guess.
Yeah, like I think it still doesn't explain. But why do the models care about the symmetry? Like, why do they, like, there are other symmetries in the training data. I don't know. You have video models or image models, and you have all sorts of symmetries that are like all sorts of other translation symmetries in video models, for instance, in the training data, and they do not preserve that symmetry often because
I mean, also,
the physics is
I think
broken.
an important thing here is that they are only looking at examples that other papers found before.
Yeah. They don't train on your model? They train on the Wikipedia, no?
I think they just the only thing that they try training is the word work. They don't actually train yet.
Yeah, okay. You mean like this? Yeah, okay.
So
like,
but also the task they are looking at is basically months and mostly months, right? They just mostly are looking at months. They probably are also looking at also the historical years. So I'm not sure how much. At least the empirical part, like, is that there's like generalizable to other things. That's okay. If you
yeah, like,
do
definitely
another
more examples
PCA axis
would be
here,
great.
is the weirder thing.
Yeah, I guess like an immediate generalization would be like rotations in some high dimensional
Yeah.
sphere, but I don't know how to-
Other symmetries. But like, there is no law that says if there is some symmetry in the training data, the models will somehow model it. There is no such general thing. That is just false. Like, we have to design symmetries into architecture sometimes, like in convolutional neural nets, for instance. And that makes it better because, like, all right, like, the whole field of geometry deep learning is about embedding symmetries. Yeah.
I mean, you could do something like, if you have these symmetries on the training data, you expect that a model that has this symmetry on the representation will have less loss.
Yeah, that's correct. Yeah, but like,
or something about the
there is no
efficiency
law.
of the representation.
There is also another thing that's like, if one paper I got angry about 2 days ago. It says the paper. It was basically saying that if you embed a symmetry into an architecture, that makes you because kill, like, not all symmetries are compatible, basically. So like, like you. Okay, maybe actually, if you have a more general model, you can just use different symmetries sometimes. Okay, okay. Yeah, I think that paper was kind of criticizing if you're embedding symmetries too hard in a too hard-coded way, which kind of makes sense actually.
I mean, if you're embedding a symmetry with architecture, you're putting you're doing some very high prior for that symmetry.
Yeah.
On the,
like sometimes it's useful.
Yeah, so something like
I don't know.
translation symmetry plus modularity implies circle. So that seems intuitive.
I think this paper could be used to design an inductive bias. Like, and like if you hardcode the symmetry in it, the translation symmetry, then it will much faster learn this exact structure. But like if you hardcode the symmetry, you will lose flexibility basically for other symmetries. That's another issue. Okay. Do they have an example for curves or just circular things? Yeah, they also have curves, I think.
They have the historical years here on the paper.
Historical years, I see here. Yeah. So they those just have different boundary conditions. Like, yeah, periodic is just wrapping around. Okay, that makes sense. Okay. Yeah, I'm gonna try to go more systematically through some example.
Yeah, but I like your idea of like taking a symmetry in physics and then finding it in language.
Like there is a like symmetries are extremely like general thing. So
also, I asked Claude, by the way, whether I sent the paper and asked Claude to think about it, and it's also talking about physics and symmetries now.
like physics is based on symmetries. I like this whole perspective, but like symmetries are still not fully general. Like category theory basically generalizes symmetries in a way, you could say. Okay. There's geometric deep learning, which is basically throwing group theory, so symmetries at all architectures. And then categorical deep learning is like, but like group theory is very specific. How about we generalize it to oblivion? Yeah, and they do that. And like I haven't seen much of throwing like group theory at representations like this that much, which is why I still want to read that, like the Niels universality paper. I still haven't read that one. I think that's basically what's one of like more general ways to formulate symmetries. And then this paper is like, if you have this translational symmetry in the thing, like if you assume translational symmetry, you derive those shapes. And for some reason, if you train a model on a training data that has these translation symmetries, it learns approximately also this shape that you can derive from just assuming translational symmetries. So like the model somehow respects the translational symmetry, which is but why does it do that? And why this symmetry works and other doesn't? Like you have video models that are like that they don't respect all symmetries. Like if
Yeah.
and why transformers? Like if you this is part some experiments which I really want to do is like take the Niels Grokking paper, which basically which is also a case of a symmetry, and like try to change the architecture in many different ways and see what has to be in the architecture such that it learns symmetries basically. Like also like could you embed it in the architecture? That's another aspect, which is geometric deep learning trying to do basically. But sometimes like the gradient descent doesn't find the symmetry. This is why geometric deep learning exists, because like sometimes if you embed it, if you have a training data that has some symmetry and you embed it directly in the architecture, then you just get better results than if you just train a blank slate deep learning model basically. And like attention is also a symmetry on its own. So like all the models we're using in most of language right now, which is transformers, they are still having an inductive bias. So it's not bitter lesson pilled enough. I think it's like I think permutations symmetry. Wait, I want to see the list. Yeah, I can show you. Like, I think it's also in here. Like, yeah, like symmetries are great. I'm obsessed with symmetries generally.
Right. But I guess
Oh yeah, I found it.
like here the distribution comes from the co-occurrence matrix, and what Vec is trying to just simulate that distribution. So I guess in some sense it is obvious that it has to learn these symmetries, at least for
I
word to
don't
vec.
think it's obvious. Like
Like
there are instances of data that have some sort of symmetries that the models don't learn. It is not this general.
no,
I
I'm talking
think that's
of
the issue. Like, okay,
like in the math, like if you assume how they're proving these stuff, like some symmetry, and then there is some structure that like follows that symmetry, then the embeddings have to be in that form if there's a unique solution. But you're saying something else, I guess. You're saying there are some symmetries that models don't show.
yeah. In this specific example, they assume translation symmetry. Yeah. Wait a second. I'm gonna talk to my dad for a second. Okay, I'm back. Yeah, I wanna try to go more specifically through some example in the paper to see it much more clearly. Hopefully. But yeah, like symmetry is good. Category theory goes even more than that. Okay, let's see. But like, yeah, what I wanna understand why some models learn this and why some other don't. Like if models would by default learn all symmetries in the training data, we wouldn't have to do inductive biases basically. So for symmetries. Like I think that's the whole like symmetries aren't all structure, but it's a lot of structure that exists. Oh my god, I want to understand more physics. Oh, whatever. I'm gonna go through example in this paper to understand what you're saying. Maybe I'm just completely wrong and just rambling. Haha. Let's see. So, and the symmetry forces. Okay.
I wanted to put the sharing screen at some point of the paper. I can do that, by the way.
Okay. Kilogram probability. Sure. They just do giant statistics over all Wikipedia. That's funny. Well, they do classical eval first, basically, you could say. It's like two different methods to get to a very similar result. I think that's one way to frame it. You either do this just throw everything into giant stacks of transformers approach, or you do this classical statistics plus extra analysis. Interesting.
But that one, the classic statistics study only works on word co-occurrences, right?
Yeah. And you have to assume the
And the
translation is
transformers. And
Yeah.
then the thing is, they see that in transformers you have the same kind of things that you would expect from the statistics stuff on the world models. The skeleton of shapes, but the shapes are not from the two word co-occurrences, because the some of the examples in transformers are completely different, more abstract things that are not about truncated co-occurrences.
Okay, I think I'm starting to understand what you meant by they just overfit it on this. It is, I think it is
I don't
likely
think
that
I know it's not overfitted, but it's still maybe not that applicable to all of the examples on the transformers. But it might be related, but I don't know.
yeah, like do they make such a general claim though?
I don't think they do
Okay.
necessarily. Well, I think they gesture towards it, but
Yeah.
the kind of how the features work. But also, the thing I was thinking of overfitting is yeah, how much is overfit in the sense of they are looking at some symmetry that they know from examples that the models represent. In this case, the the model represent the distance between months in some way.
You mean like you want more stuff than just distance between months? You want
Yeah, I would want
you
to
want
see.
like more complex.
I would want to see, doesn't need to be more complex, things that are new, that are not from that are not from some paper that has found that the mods have this nice geometrical structure, or that
I
days
see.
of the week has that structure. Seems like it wouldn't be that hard to come up with some extra thing that you expect to have the same structure and just find the same thing by doing a PCA on it.
So okay. If I get you correctly, you're basically saying this theory has only this descriptive power and it doesn't have like predictive power. So like it is able to like explain like retrospectively explain approximately explain parts of existing phenomena, but it's not generating new testable predictions.
Except like, maybe here. Depends on what they did here exactly on this example here, where they say
I think you can generate
novel prediction or theory when projected into peripheral components where embeddings display listener questions analytic prediction by proportion C. Linear cross can code. Yeah, I'm not sure I understand this one, but apart from that, it doesn't seem like they did a lot of new predictions to new things.
Yeah, like I think you can do more predictions for more things, but this paper just didn't do much. So like, I think this theory has a predictive power, but it's not being explored.
And when
sorry. For example, like king minus man plus woman equals queen. Right? That can be proven.
Hmm.
But I don't think they have done like that kind of symmetry.
Yeah. Like,
Do they?
but
Yeah,
I feel
like
like that will also be an example of a thing. Well, at least the case that we don't see the representation. There's another example of a representation that people know about, right? Can they? Is there some symmetry that you can come up with, some set of things that have some symmetry that no other paper previously has thought of looking into that, and you say, okay, so there's some symmetry on the co-occurrence of these tokens, therefore we should see this shape. You look at it and see that shape, right? Rather
yeah,
than
like
because this plot already existed. Like they cite a paper that already showed. I have already seen this plot multiple times with for the historical years, right? And this is the same circle for the mods. I already knew they were circle. I made memes about this, about the circle
Yeah.
thing, right? So I feel like if their theories actually works, it wouldn't be hard to showing another example. That
like
is
they have
new.
like yeah, like I think what you might be able to do is take just if you do the co-occurrence analysis on the training data, you could possibly find more shapes like this in there and see if the models also learn it. And that would be like new predictions, basically.
And I can see how the math can be. You could just from the math from this case have some nice results and say generalize. I guess parties I don't understand it, but parties I just generally skeptical of very big piles of math that I don't understand, that don't have new predictions, because they are often just wrong in some subtle way. I will take a lot of time to figure out. Right.
If you would generalize translation symmetry to literally arbitrary translation symmetry into training data, maybe this model doesn't work because you have video models that don't respect translation symmetry of objects.
Yeah, but
maybe you just need more data and more compute.
or I mean, maybe at least it feels like maybe models don't represent all of the symmetries, right? But you should expect that they represent more symmetries than most and historical years. And you should be able to find one by trying a bit. Like maybe they can't do that and they'll do a future paper. Like, but they should you could come up with some examples, look at them, and maybe some of them just the model didn't learn that to represent a symmetry. But at least you should.
Maybe there is like some general way when you look at the training data, you derive all sorts of symmetries in there. But like here they assume the here they work with this translation symmetry. And like you could maybe find much more symmetries and see if the model and derive some shapes like this from it and see if you find the same shapes in the training data.
And how much this is
in the models.
In some sense, some trivial statement that only works for just doing the Word to X style thing. And if you do general transformers, the efficient way of calculating the symmetries is trading out transformer on them.
No. Go ahead.
We can like replace assumption 3.1 by some other symmetry, like general symmetry group, and then we will get proposition 1, but we have to like derive the conclusion instead of like a circle or some other structure.
Can you explain what proposition 1 actually says? Because I don't think I understand it like more in detail.
Yeah, it's basically saying that if you assume like translation symmetry in like your words, a subset of your words, and then like it's positive semi-definite and all these assumptions, then those word embeddings have to be on the circle.
And why do they have to be on the circle?
That's the proposition 1. Look at the proof.
Okay, let me see.
Like, how tautological is this kind of proof of, like, it's just making enough assumptions that
Yeah, yeah.
So you first assign coordinates. And for instance, let's do months. So you have an interval 0, 1, 2, 1 with that's like periodically wrapping around. So like January is minus like minus 11 divided by 12. February is minus 9 divided by 12, and so on. So like you get this periodic wrapping around. Then you fit the exponential kernel. Let me see. I think the best way to understand is just plug in as many examples. So I'm trying to do that. Whatever. I'm constantly skipping around the paper, and that's wrong. I have to go from the beginning when it comes to the example. I just want to write, like, this is, I think, the best way to learn Mafi papers. You take a specific example. So I want to take two examples. I want to take the circular months, and I want to take the what is it called? The years on a number line. And then you just do all the math and you derive from the very beginning, from all the assumptions, you derive the result. And I want to do that now. Okay. And not skip around. So let's try to not skip around. So let's go. At least that's how I'm learning most of physics and ML math. Okay. This might be... okay. No special relationship. Oh, I see. I see. I see.
Oh, wait a moment, I have to go open the door down.
What did you say? Okay.
Someone is calling, I have to go check. I'll be back in a moment.
All right. I'll just go through the example. So, normalized co-occurrence matrix. Clever measure of surprise. Numerator Pij minus Pij. So you have unigram probability. You have, what is the first one? You have co-occurrence probability and unigram probability, and you construct the matrix by co-occurrence probability minus unigram probability of both divided by. Okay, that's interesting formula. How much more or less I and j co-occur than expected change by chance? Okay. But I like this paper. Let's go slowly. Oh, they specify that in the appendix by the context window. Given hyperparameter represents the context window size. They use Crocker. Oh yeah. Crocker delta. Yeah, that's from physics as well. I know that. That's used in what was that? That was also some circular thing. Where did I use it? Angular momentum, I think. If you do Poisson brackets, oh my god. I'm just having joy from seeing math that I saw in physics. In theoretical classical mechanics. Okay, whatever. So
I
every
know that
occurrence of January. Oh, go ahead.
like all representations of the cyclic group have to be like this on the unit circle, like this nth root of unity. Like if you represent like a cyclic group
Okay,
in like
I'm back.
in some vector
Welcome back.
space and as representation, as like group of representation, it has to be like nth root of unity. Like that's a
Also,
theorem.
Yeah, there's a. Huh.
But that's not always true for like other groups. Like other groups can have like more
Yeah.
representation.
Only for cyclics, it's by definition
Yeah.
they form a cycle.
Yeah, cyclic group, like
Well,
the representation has to be like that.
yeah. Also, by the way, Victor, there's like at the very end, like I'm now trying to dissect it more, and like how they compute the what is it called, the co-occurrence probabilities, and they use Crocker delta, which is used in theoretical classical mechanics. I haven't seen it in AI yet, I think, which is very cool.
So, anything interesting you
so
have
they
figured
use-
out since I was not here?
Yeah, I'm now going in much more detail, step by step.
Also, if you want to, maybe you should. Since you are the one looking at it now, maybe you should share your screen because I'm mostly not sharing anything specific right now.
Okay, that's one option as well. Basically, what I did is I prompted Claude to construct an example by plugging in concrete numbers into the formulas. And the only thing that's needed is that Claude actually extracts equations from the paper and doesn't hallucinate any. So that's a very specific thing there. This is mostly how I kind of want to write it down and just plug it into Wolfram. I should automate this process by screen 1, I think. Yeah, let me see if I have everything. General channel. What? Okay, good. Yeah. Screen 1. I think I'm still gonna change it a bit. So explain the paper in math using example, explain all the technical math. Assume this is also good. If you say assume a little background in math, it will just define absolutely everything. So it might also define what is a matrix, but explain all the math, extract all the formulas.
Let me close my thing and put the recording on your thing.
Yes. Quote them
Okay.
with source.
Oh, thing. Okay,
Think-
never mind. It works. Also, do know that your screen is being recorded, so don't show stuff you don't want to be shown. I mean, I can always delete them from the YouTube video later if it's something really bad happened, but you might not notice stuff. So
Yes. All the in detail. Extract all the formulas and code them with source. I think this is good. And
if you have a second screen, you might want to do stuff on the second screen, so it doesn't.
Yes, that's what I'm gonna do now. I wanted. I've read. Good cloth, pet. I want what I wanted. I wanted the paper. I think it's this one.
Oh, you should download it and send it to Claude because if you just dig
That's what I
the
did.
link, it has. Okay, yeah, I tried giving the link earlier and it had trouble getting it because there's understandably our ship has rate limits for the Claude.
Yes.
Yeah.
I kind of wanna say yes. Going with source. Don't forget anything in the math formula. That's important to the explain the method, the math behind the method they use by plugging in concrete numbers, by plugging in 2 examples, plugging in concrete numbers, and explain all the technical assume. It's important to the derivation, to the whole derivation. Okay. This is good. And this way, Claude also like... Okay, they do that here. Like basically here just they throw the equation and they don't show an example here, I think. Yeah. Like, here's an equation. I think it's better for any math in general if you throw an equation like this to just directly show some example. Or at least for me, it's better to learn it that way. I'm really liking this. But I don't think symmetries on their own can derive everything. Like, there is just much more structures. But here, like, in this analysis, you have to assume to use some symmetry still. And what to look at, so you look at seasons, for instance. You could traverse the space, but it seems like a great frame. Yeah, here they use like... This is a Fourier transform, right? Yeah, this is a Fourier transform.
Oh, you have music and it's but yeah,
Is
that's
it playing?
Yeah, but
Yeah, you
if
can just mute the stream.
yeah, I
you
also
click on
muted in the recording, but maybe the music is a bit on the recording.
Whatever. It's yeah.
As long as
It's
we don't get
it's
copyright
just
claim
electro.
because of it. Yeah.
This is
I was
highly
thinking,
copyrighted music.
I was thinking, who is raving? We are still reading.
Yes. I'm now using Claude to plug in concrete examples into the math, so that I see it more. There's so much math down. Like it's 45, 35, 34 pages. Like and everything but I like that. I want heavy math in this domain. I explicitly was thinking a lot about like this is exactly like
this is a very
the
poorly coded paper you're saying.
Yes. like derive the structure of the what the model learns, like analytically. That's like holy shit, amazing. But you theory word amazing. Okay, there's more in the appendix. Deltaware Mission Oklahoma. Wait, did I mention? Yeah, I did. Okay. You see that this theory is, it's still like there's more structure still. Like theory, it's just too smooth, in a way you could say, which makes sense. So like the models are just more still. There's more structure there. It's not just the symmetry, but like that's what you do in physics. You're like assume the skull is spherical and no friction exists and so on. Like this is very physics coded paper. Oh my god, Claude is still going. Okay, that's gonna be juicy. Help reconstruction with seasonal words. Correct form. Tensor component. Spectral decomposition. They're using Walsh character. What the hell is a Walsh character? Wait, what? Math. Walsh function. That's in Fourier analysis. Okay. I just feel like Mech Interp is reusing so much This is why I'm so happy about it being framed in math like this, because when you Google all the different terms used and formalized, you find out, oh, it's used in this field, in this field, in this field. Okay. Claude generated it. Let's see. So, why do language model represent cyclic concepts as circles, timelines, curves, geometric locations as decodable coordinates? Because pairs of words that are close in time and space. In time or space. Okay, I see now. Tend to appear together in text more often, and this pattern has mathematical symmetry that forces the model. Not all symmetries do that. Whatever. Say again.
Why
That force, yeah, like, yeah, that's what I'm like. Not really, but yes. Like you can derive the theoretical structure from the
But like
symmetry,
in
but
this
like
sense,
why would the
so
model train it, learn it? You know,
yeah,
there's
like
no rule that it will
what
learn all the symmetries
forces
in the
the
training
model?
data.
What things are you assuming about the model that leads you to conclude that it will have that structure? That is optimal in some sense. That is representing the symmetry in some sense, or what exactly?
Like if you would make such a claim, I think you would have to basically do like physics over the training itself,
But
and
what's
like
the wait?
somehow prove
What
that,
I
but they
want
don't do that, I think.
to understand, can you explain how, like, how do you get from some structure in the data to this to the
Shapes.
structure to the shapes? Yeah, where do the
Yeah,
shapes
that's what
come
I'm trying
from?
to see as well. Yeah. And I think it's best understood through the example of like just numbers running through all the machinery, and also the proofs basically.
Because the
Text
proofs
corpus.
are
Let's see.
supposed to not be about the machine learning. Right? They're supposed to be about some more general thing that is about the.
Yeah. Let's see. You have text corpus. You count word co-occurrences. Yes. Then you build matrix M, which is the co-occurrence matrix. Notice M has a translation symmetry. Notice, don't you assume translation symmetry? Okay, let's see when it goes through the math. And also double check it in the paper. Proof eigenmodes must be sinusoids. So that's the proof. Okay. That was the proposition 1, right? I think so. Define blah blah. Project embeddings have Fourier geometry, so that should be this part. Predict exact embedding geometry, validate on real models. Okay. 4 seasoned and 5 historical years. Sure. Yeah, see, they if you do this, Claude is like, okay, here's what vector is, here's what matrix is. That's beautiful. Whatever. From scratch, yes. Whatever. Vector is a vector that transforms like a vector.
It's becoming a tutorial on
Whatever.
how to use Claude to understand math.
Yeah. Transpose, dot product. Okay, gram matrix. Set of vectors. Yeah, all pairwise dot products. Yeah. Yeah. So norm, Fribrius norm, total size of a matrix. Yes. Yeah, eigen stuff, eigen decomposition. Yeah, you just decompose it into the different eigenvectors, right? Spectral composition is the same. Oh yeah, okay. So all the transformations that positive semi-definite, all the transformations, you have to have a symmetry matrix first. And all the transformations are just positive in a particular direction. Okay. Whatever. Or in the different directions by the different eigenvectors. Okay. Yeah. If I remember correctly, that symmetric matrix is just that it has symmetric. Yeah. Yeah, okay. I remember correctly. SVD, PCA, rank. Okay. Extract Young-Minsky theorem. If you want the best rank D approximation to the matrix, you just kept the D largest single. Okay, yeah. I didn't know it. The name is like this, but yes. Fourier transform discrete is just on the discrete data. Yeah, degenerate pair. Okay, same length. Sacral matrix. Was any of the other any other of the Fourier papers using this term? Like this was everywhere in the other papers. I'm not sure if the other papers just use the math term itself. Yeah, circular matrices was diagonalized by the Fourier basis. That makes sense. Two-Lipschitz matrix. Matrix where each diagonal from top left to bottom right has the same value. Okay.
Okay, I think
I also don't know this term.
According to Claude, by the way, if I understand it correctly, this comes from the assumption of the thing that the other paper, like the one that says that work to back training is approximately equivalent to finding the low rank matrix factorization of the thing, and I think of the co-occurrence matrix. So I think this is just saying if you have a low rank factorization of the concurrence matrix, it's going to have this geometric shape.
If
Is
you
this a explanation?
on the training data, the first thing, it's still you predict the shape from the training data by doing statistics on the training data.
No, but I feel like this the idea here is partly that they are you can do it from the training data if you have the. Well, wait, let me read a bit more. I'll try it again.
Do they look at the transform architecture in the first place? Yeah.
No.
I'm
talking about the
yeah. Let's
word
see.
to back.
Reusable what happens at the edges. Periodic boundary condition. Yes, they're using the word boundary condition from physics. That's also interesting.
Okay.
Okay. Convolution
Okay,
kernel.
let me go back to section 2.
Section 2.
For a moment. Yeah. That was something I was missing. Go to section 2. Like I think your thing may be frozen for a moment. Wait, let me. Yeah. If you look at the perimeters and related works, read the thing after the this key result, like on a bit down there. Yeah, at the bottom, this key result.
So you mean this thing?
A bit more. You can read that and then. No, not that. Preventing the word embedding geometry. That section, especially the paragraph.
Two tokens argue with simplest. Two word embedding models such as word to vehicle, like exclusively from this statistic. From. Whose I throw V is the d-dimensional embedding vector for word Y. Okay. In recent work show that such models learn to represent top eigenmodes, approximately equal to the pointwise mutual information matrix. The learned embeddings are this. Okay. I think I might just give it the other paper as well. Since it proves an analytic link between co-occurrence statistics and the learned. So I thought this paper is actually doing this mostly. Aha, although this result gives exact expressions for the learn embeddings, it requires numerically diagnosing M star in general in certain cases. However, M star may be dominated by a simple structure as able to analytical diagonalization. Okay, so they just find a way how to do the numerical things analytically in this paper then, compared to the other paper.
Okay, but then the structure here comes from, if you say that the word embeddings are just learning this matrix, you can show that the representation will have that shape or something like that, right?
Say it again?
So is the idea, is the whole paper like showing, if you assume that the models are learning this matrix, there are things you can show about that this matrix will correspond to those geometrical shapes for different concurrences.
Yes, they derive from the matrix. They derive the shapes. You build the matrix from the work occurrences. Notice that the matrix has a translation symmetry, and through that derive that the eigenvectors must be sinusoids.
The problem is this is the problem with extending that to more bigger models and the other kind of things is that but then you should be able to show this on as easily on other examples, like you could just do that, but
yeah, like I don't think they say you need to have a deep learning at all as well. Like they just have a different mathematical formalism to get the same shape that we measure in the transformer
and
models.
it's complicated to explain how this relates to the to the actual machine learning stuff, because the bigger models are not just learning the are not just learning the co-occurrence matrix. They are learning some more complicated thing.
Yeah.
They are also probably learning the co-occurrence matrix, but yeah.
Like as I understand it so far, that like functionally there is some sort of correspondence like this for when you're looking at translation symmetries between using this method to derive the shape and just training transformer and looking and reverse engineering a similar kind of shape. Like there's this correspondence between the end result of those two methods. That's my current understanding. And I wonder if the proof itself is like, actually it's somehow more connected. It's not just functional equivalence. Because there are many different like mathematical ways to compute the same output from the same input. So, and yeah. And so that's what I'm like wondering if they use in any of the proofs some like, oh, the transformer is just doing this kind of mathematical thing or whatever. Or it's just, hey, we have a mathematical model that predicts the same shape from the training data, just like if you just train the transformer and reverse engineer it, the shape. Yeah, like that's what I'm wondering about. Okay, latent variables, sure. Lisieux curve, a parametric curve. Have you heard about the Lisieux curve before? I didn't. A parametric curve of the form xt xyy.
But my Claude also mentions it, so.
It says in the paper. Yeah. Looping, feature 8, or pretzel-like shapes, depending on the frequency and ratio. It's a general shape that you can construct. And these shapes just correspond Yeah, it's basically just this function. Yeah, it's a very sinusoidal, very Fourier. Describes superposition of two perpendicular oscillations in x and y directions and different angular frequency. I wanna play with this function a bit. Is it on this MOS? Of course it is. Yeah.
Wonder, should we
Yeah,
stop
this is
the
super
recording
cool.
and all that?
I'm up for like still figuring out all the different math terms used on the recording, but up to you.
Ah, yeah, okay. I guess if you want to do that, we can keep the recording.
This curve is cool. Yeah.
And this is now Bernie trying to figure out the paper. I don't feel like doing that right now, but I am interested in seeing you do it.
Okay. This curve is interesting. If you have this general shape that just is, and all these are like special cases. All these curves are special cases of this. Oh, infinity. Huh. Then that's
but
that's
is
a
this
very useful
not just
mathematical
a
formalism.
sum of sines and cosines?
Yeah. On x-axis you have a sine wave. On y-axis you have a sine wave.
So is this again?
But
That's not the kind of thing you get from the from the same kind of thing as the Neil model thing, and this Fourier sum of.
that's a special case of it. Yeah.
Yeah.
You have plus c plus d. But why do you have plus f here? Oh, okay, f is... Oh, you want a specific f like this. Do they define it? It has to be... Oh, interesting. If you have a ratio a plus b, figure is ellipse with special cases including circles and lines. So this is a very, very general mathematical structure, which as a special cases includes lines, circles, ellipses. So it makes sense to use it in this context because yeah. This is a general theory, basically, in this sense. That's pretty cool. Pointwise mutual information. Okay, I know what is mutual information, but pointwise is... Okay. How much more or less do words go core? Compared to it's very independent. So this is if you look only at them, and this is when they look together. Okay. So this is dependence and independence. Right. You are measuring that pointwise mutual information. Why is it called pointwise? Yeah, makes sense. The of two discrete random variables refers to average PMI of all possible events. How exactly do they differ? Here you use scale divergence. Here you don't use scale divergence. Okay, sure. And you put it into a log. Okay. Slide window is a sex file across the text. How the different words correspond to each other. So let's see. It's starting from an equation in appendix. All right. Equation 19. Oh yeah, I think it's the one. Wait. equation 19. How is it written? Why cannot I find it? Index a dot 2. Let's go manually then. Or wait. No. Or is there a... If I open it in archive, will I have table of contents? Here I have a table of contents. Good. Okay, that doesn't help much. I just wanna find this equation. Appendix A, okay. A1, A4, A2, A2. And this one. This is a crocodilta. Yes. What it means in plain English. Funny. So, do they define it here? So L is a context window, F representing the state space rewriting function. The co-occurrence Skype distribution Pij is defined. So we have Pij. Okay. Crocodile CV you have here. CVD. With word in the corpus. So we have a with word in the corpus. Then you take the delta and take the y. 1 if the with word is a word y. 1 if the and 0 otherwise. Okay. Okay. FD L plus 1 minus D is a weight that gives more importance to close words. L plus 1 minus D. And what is D? Do they define D anywhere? A distance. Is D a distance? Here is D a distance. I think it's distance. That would make sense. Let's just double check. Yes, D is distance between the two words in the text. Okay. So you have a text and you just take this. Okay, sure. Z is a normally constant to all the probability sum 1. Sure. So we look at each occurrence to the right, then look all the words of within L positions to it. The unique probability how common a single word is. Okay. Spring and summer, fall and winter. Whatever. Adjacent season, spring, summer, summer, fall. A co-occur more than distance one, spring, fall. Spring, fall. Also notice the circlet-like structure. Each row is approximated by a shifted version of the previous row. Each row. That's true. Yes. And I think... Okay. Yeah, in-game probabilities is just this. How common they are. Yeah, this makes sense. Historical years. Five historical years. Only 50. Yeah, this is just lines. This is not, and it doesn't wrap around, sure. The normalized co-occurrence matrix. So then they go here. That's an equation 1. It's in here, right? Yes. Yes, yes. Okay. How often words ing actually occur? That's here. How often they would co-occur if they were statistically independent? Denominator divided by 2. Pij. Normally that keeps the values bounded between -2. Okay. -2 and 2, shouldn't it be -1 to 1? Whatever. Doesn't matter. Okay. Now it skips to equation 23. M star is very close to the PMI matrix. I guess that's because it's of computability. Right, log is just minus. Hmm. Oh, alright, there's this thing, okay. Never mind. So, if you have PMI like this... Oh, another paper showed that it's... Okay, sure, so we have this. Huh. Whatever, this doesn't matter much. They use Taylor expansion to see that Mij is very close to the PMI matrix. So it's kind of computing mutual information approximately enough. I mean, it makes sense intuitively. With some error. Hmm. Actually curious, let's see. So whatever. Computing M star for the 4 season. So M star is the mutual occurrence, basically. P spring summer, P spring times summer sure. Together they spring and summer are close. So alone they are like 20%. Together independently they are lower. So that makes little sense. So together they should happen more. Numerator, so you get the probability together minus probability on their own, and probability together is a bit higher, so this is the extra togetherness, and then you normalize it by this fixed number. Yes, and you get this share. So you get this number, share posit seasons. So if they are together and not together, so together very rarely, in general relatively often. Sure. So this is the full matrix. Matrix each row is associated where the value depends mainly on distance between seasons. Wrapping around. Here it's explaining embedding. Okay. Is approximately quantity on the objective in equation 20. Self-outer product. Oh. Oh.
Oh, by the way, I noticed something. I think they, if I understand correctly, they didn't train a model, the word-to-vec model. Like they just calculated the matrix directly. But
Yeah, I'm just looking in something similar, I think.
that seems bad,
think-
right? Like I confuse. Shouldn't or shouldn't they train the? I'm confused by. Didn't they test with the word to vec if it matches the thing? What is how it was the word embeddings that they show on the first figure on the second thing? How are those trained actually?
You want. Now I'm looking at the learning objective that they learn. I'm not sure if you looked at the stream or if you did that
Oh
on
no,
your
I
own.
was on the paper. I was on the paper also, maybe looking at the same place at the same time for similar reasons.
Right now,
was
I
looking
think
at-
that's what happened. Yeah.
Yeah, I think in word embeddings, appendix A point 2.
I'm at B1.
Oh yeah, but yeah, that one is the sum. Yeah, that one points to yeah. See appendix B for yeah. It's appendix B. Appendix B is like the more detailed explanation of that.
That's where I'm at. Yeah.
Yeah, I just happened to be looking at the same place because I was talking with Claude, and also I said some things, but I forgot I was muted. But
Oh, you were muted. That's why you weren't talking. Okay.
apart from that, I also was distracted just talking with Claude about the paper, and I got a bit distracted
Okay.
looking at Twitter at some point, but then went back to the paper. So
I
I
see.
don't know how much this will be interesting to people watch to watch the recording, but
I think it might.
I do feel like people who were here might have not that interesting the ones that were here. Maybe I need to pick a different kind of paper for more people that are less into math to contribute and talk, but we'll see.
I see.
Also not pick it last minute, but that's another thing.
At the same time, I like Mafi papers, but yes.
Yeah, but I guess we can do a mix.
Yes,
I guess
yes.
this was a Burnie paper. I can pick another paper that is less.
Yes.
Uh,
And yeah, I'm just looking through. Like, I think that's maybe the key on how they. So they calculate the embeddings basically instead of training them.
oh, but
Oh no, they wait. They have a loss. No wait. Is this this is the learning objective? They learn this matrix. Each row v1 is word i's embedding vector. Is this how the? No, this is approximating word to vec.
okay, but is the
They are-
word to vec in word embeddings in figure 1 an approximation of word to vec or actual word to vec?
This looks like an approximation. Like the training, the learning objective. Is this the? I think this is the learning objective, right? Producing this matrix factorization problem. And how do you do this minimization?
Okay, yeah, the word embeddings, according to Claude, is the thing and you're saying, and no, that's for word to vec, and this is so the key to what happens with the maybe transformers don't learn like maybe the model don't learn the training. In this case, they are solving that by not training any model and just assuming it eventually converges into this thing. And it approximated the thing they show in a different paper that it converges to supposedly. Yeah.
Converge. How do they
They don't do
define
that. They just kind of assume that the model will represent the matrix, if I understand correctly, right?
converge with high probability? I mean, it's a different model trained with different, and it's like, does it converge for all possible training data? By Edskart-Minsky theorem, the trained embeddings must have the structure up to semantically irrelevant. How does this theorem work? Write the eigen decomposition. Where are eigenvectors as column and why is diagonal with eigenvalues? Sure. by the Minsky theorem, these will the best rank. The approximation keeps only top D eigenvalues. This is equation 24. Show 25, 24. So now this one. Why would they not train like normal Vortuvek with gradient descent? Why do they do this mental gymnastics or whatever? That's what I'm a bit confused about. Or why do they not train both? Like, is it simpler, or like it seems kind of weird that they chose this learning objective. They chose the learning objective to be as close as possible to the thing that they are trying to prove in theory. I'm so confused. What the fuck? Maybe I'm misunderstanding something. V is the optimal value. Okay, so this would be the optimal value. Which corresponds... Yeah, I think I was misunderstanding. They don't train this one because this is the optimal value. And the Vortuvek algorithm is approximately equivalent. What showed? Do they just cite another paper that shows that there might be actually doing that? Yeah. Closed form training dynamics reveal hidden learned features and linear structures in Vortuvek-like models. This is also 2025. Oh my god. These models learn orthogonal linear subspaces one at a time. I think I just found some even more general paper. Each one incrementing the effective rank of the embeddings until model capacity is saturated. I mean, this paper is basically saying that Vortuvek is having the orthogonal linear subspaces, but like we know that when we do this on big models, we need to use something like sparse autoencoders because you have the whole problem of superposition and you have to disentangle the different linear directions. So so the issue is like This doesn't work for big models. I think there's this assumption that if you're using Word2Vec, they don't deal with superposition.
Yeah, I mean, but they're trying. I mean, definitely, they do say it doesn't work for big models. They are saying something like, you do see these shapes on big models, and it's maybe related to the shapes showing up naturally from the co-occurrence matrix on this. Well, from the co-occurrence matrix, not Word2Vec, because they are not even looking at Word2Vec. They are working about their theory of how Word2Vec works and what it approximates on the limit, which is the co-occurrence matrix.
Why do they? Yeah, like this would be the perfect. Sure. But why would it be perfect? Wait. Optimal value. Why would this be the optimal value? That's an assumption they make. No? Word2Vec was developed by Tomáš Mikulov. That's a Czech person. Hell yeah. He worked with Ilya and Jeff Dean in Google on Word2Vec. Oh shit, okay, I didn't know that. That Ilya is and Jeff Dean. I think I just knew the Czech scientist was behind Word2Vec. The F column of the embedding matrix equals the UF eigenvector of M star. Scaled by the square root of an eigenvalue's absolute value. Why do they suddenly use... Oh, that's from the spectral decomposition, right? I think in order to understand it, you have to read a paper that says approximately, where is it? That the word-to-vec algorithm is approximately equivalent to running
Yeah,
rendition of the
I
objective in this
generally
equation.
also get into that talking with Claude, where Claude just said that I was asking it to summarize the thing findings and told it to us what might be wrong, and he basically said if that thing approximation is wrong, then the whole thing is wrong.
Mm-hmm. Yeah.
Also, that approximation is wrong for transformers, so it's then clear what we can extrapolate from this to actual transformers.
In general.
Instead, that
This is
maybe
just the
there is
embedding
some way
matrix.
to make those shapes is related because related, but it can also be as Also there is a thing the assumption 3.1 is apparently not, according to Claire, violating in real data according to appendix B3.
What's with the assumption?
Specifically, B3 says that
That's the translation symmetry assumption.
yeah, the positive and definitive. Yeah, this assumption is violating real data. Indeed, the empirical impression in Wikipedia has unimodal distribution peak near. The exponential kernel in figures 1 and 2, the exponential kernel estimated and fit into M star does not strictly speaking represent the kernel in the Satori factory, which should be measured for this space with typically determinate quality predict the absolute scale of mode amplitudes. Display this pressure of quality of perspective correctly predict for relative amplitudes when the models and the wave numbers. Yeah, this actually these assumptions don't even don't are not like the symmetry doesn't work like that in the Wikipedia data, if I understand correctly, right?
Let me guess to it.
It's on B.3.
B.3. Weaker version of 3.1. Oh. What? But still, it appeared to correctly predict both the relative amplitudes between modes and wave numbers. What? So the assumption is wrong?
Yep.
To develop theoretical systems that more faithfully model real data. Okay.
But you can go back to where you were and we go to this instead of jumping.
Yeah, I'll get to this part later, I guess.
Yeah.
This is a projection, right?
Also, this exponential kernel. Okay, yeah.
How are you guys doing? Are you still recording?
Hello.
Yeah,
Yes, trying
although,
to figure
although
out
it's
what the hell
not.
is happening in the math.
Yeah, although now is basically a recording of Bernie asking Claude about the paper and trying to figure it out, which is maybe not as interesting. But I guess if people are not interested, they'll just stop recording.
You guys are still talking about the paper?
Yes. I want to understand this paper. I will be reading it until I feel
Okay,
dropping
once
in
you
my
figure it out, I guess
neural
you could explain it to
transformer.
us later.
Yeah, I'm right now. I'm still also asking Claude questions. I'm mostly just watching Bernie do a gameplay of how to write a math paper.
Yes. Like you can make Claude go from scratch, explain all the math terms, and put in all plug in concrete examples, and just go through it from scratch step by step. Then everything Claude says, you Google it, and you also look at the paper and see if Claude is bullshitting or not.
Yeah, I see.
So it's
Claude
like
summarizing
I
the
use
paper
it.
for you?
It is not a summary. It is more like reorganization of the information, of like take all the math in the paper and like explain everything from scratch. You plug in the examples in the math in the paper step by step, like don't skip stuff. And all the information that Claude says can be found either in the paper or if you Google the math terms, if it's explaining math terms.
I see.
That it's not in the paper or in some other papers when it's referencing other papers, basically.
Okay, I'll come back.
So like in order to minimize hallucinations, you basically double check everything this way.
Yeah, I'll come
because
back
I
in
don't
like 10
trust
minutes.
Claude. Okay. The final trained embedding matrix. Are you sure, Claude? Isn't it like optimal theoretical value? Yeah, and Claude was just right about one definition. So it's good to double check. Taking eigenvalues and scaling them to the square root of the corresponding eigenvalues. So you do eigen decomposition, eigenvectors. Yes. What? What? Is this used in linear algebra? Do they use is slicing method notation used in math like this? I cannot recall I've seen it like this before.
I mean, it's
Like
definitely
they
a
use
thing on
slicing
Python.
notation here. Yeah, it's in Python, but it's not in math.
Maybe it just comes from math. I don't know.
Matrix slicing. No, that's not how you slice it in math. Ah! They're mixing Python in math. Oh my god. That's
Obviously, the
I'm just
Python one is
looking at this
superior.
completely confused what doesn't mean, and now I'm figuring out. It's they're just putting Python into linear
I mean,
algebra.
to be
Hell
fair,
yeah.
I expect the machine learning people will understand it better this way. I'm happy for it.
Yeah, probably. But like I just was looking at it for the past 10 minutes, completely like what, and now Claude is like, oh, it's
Like
Python notation. I'm
the,
like, okay, that makes sense
the
actually.
Python notation was designed for people to understand it.
Yeah. Oh my god. Okay. If Claude isn't hallucinating, let me double check. You take all of those and first D columns. Yes. First D eigenvectors. Oh right, yeah. It's correct. That's how you want the top eigenvalues to be in the vector matrix. All right. But wouldn't like, this seems weird to me. Wouldn't you like have the other eigenvalues kind of leaking? Must have this structure. This is wrong, I think. It converges to this, I guess. What does it mean must have? I guess that means approximately, because it converges, but I don't think it converges in the limit. Oh wait, I wanna read that one paper that is like having this assumption about Vortuweg being equivalent to this. This seems to be underlying the whole paper. I'm just gonna like save it for
I
later
mean, they
because
do.
I don't want to
They
get
do.
into.
li-
Go ahead.
Sorry. They do literally
Go
say
ahead.
this assumption underlies the or results. Like they do say it underlies the whole paper, like very clearly on the
Hmm.
on section 2 in preliminaries. This key results underlies our theoretical analysis, since provides an analytical link between correct statistics and learning embedded geometry. That's the sentence I mean.
Let's check that paper later, because I first wanna go through the example. But like
Okay.
I'm still why, so I cannot continue. No, let's go through the example. Let's assume that's correct. But like if I assume that's correct, then the rest of the paper is boring. Because that's just deriving from it, I think. Let's see anyway. So
I mean, I guess the paper could be interesting if it says that you can derive it from that only, and you get these shapes.
like that seems to be correct. At least for Vortuweg, because this is only proving for Vortuweg.
I also, how much can you actually derive the correct shapes even for Vortuweg versus there are some details that they are overfitting that to show similar shapes? Is the question I have. And
Yeah,
I don't know.
makes sense
Because
as a question, yeah. Okay, so sure, it will be as close as possible to this one. So the And they say M star. Wait. M star. Oh, must equal. Wait. Equation 24. They equal it. They equal it. What do you mean? Are we in physics? I forget. Like I used to do some pure math, and I still to this day cannot comprehend how in the same paper they first like say it's approximately equal at one part, and now they equal it. They say it no like that the V star converge, that the Worteweg algorithm approximately converges to V. Wait. It feels circular. Okay, I mean, I guess so. Okay, actually, maybe, the trained embeddings must have the structure. Approximately, write the word approximately, and I'm gonna be happier. Wheeler's the largest D positive eigenmodes. Okay. Sure. The symmetric version, equation 20, can only produce eigenvalues 0. Both V and V star. MSD.
What do you think about? Let me send
Oh,
this. What do you think about this thing? The last thing I sent you on the DMs. That is from Claude.
let's see.
Does it make sense, or did I just hallucinate that?
F. I had to bet. Wait.
And if
Oh,
there is a I miss an I.
the second thing that you sent.
Yeah, the second thing, and that one. Yeah. The first one is also interesting, but it's,
Different. I'm reading it now. Interesting.
I don't know how much this is.
If the true kernel is significantly non-exponential, would give wrong frequencies. Like, that makes kind of sense since this is like.
Also, what do you think about the
Like there
first
are
thing I sent?
deviations. There are deviations in the theoretical predictions from the empirical results. Like that's a very common thing in science, I think, and
it's also from
would make
the theoretical, even for the predictions with their with the metrics from Wikipedia. They are not even from word to vec.
huh.
Right? Like
Okay.
at no point they take actual word to vec. They just take this their idea of that word to vec will converge to this matrix thing, right?
Yeah. They assume that. Well, they don't assume that. That's proven in the cited paper, apparently. I will read the cited paper.
But also before that, what do you think also about the other thing I sent, the previous paragraph?
One of the papers makes interesting concurrence versus this is statistical phenomenon. Geometry is imposed on it by the structure of the data.
Contest, I was talking about the other, the West Gurney thing and the content task.
Yeah. Geometry is imposed only by structure of the data. Yeah, it doesn't need to rediscover the circle is mathematically inevitable consequence of factoring a circle length matrix. I'm confused a bit here. The other computation. When a task requires modular and predict, Destin discovers the circle representations make that computation implemented by inline assumption. Here the model is active. It develops the geometry because it's useful for solving the task. These two the same manipulated PCA. They arise completely for different reasons. Different reasons? In the module, we know
I'm
that
not
the
sure if
model
it
uses
makes
a
sense.
circle because, yeah, I feel like it doesn't make much sense actually. Maybe I just need to think about it more because the circle only exists because the model built it to do the computation. In the co-occurrence case, the circle exists whether or not the model uses it. What do you mean uses it? As in,
I think
you observe, you can do. Yeah, I think Claude is kind of confused. It makes a distinction that doesn't make much sense to me. Like in both, you can use this Fourier craziness to get the shapes in a way.
Anyway, go back to the other thing. To reading the thing. Sorry.
Yeah. Actually, maybe Claude makes sense. Maybe Claude is like, is it only for embedding or is it also for temporal reasoning? I think that actually Claude maybe makes sense in this direction. But it's weird wording. So I think it makes sense to think about, is it just embeds into the circle and then does whatever non-symbolically, or does it embed into the circle and then do the trigonometric algorithm that's in the Niels Grucking paper, basically? Yeah, I think that makes sense to ask. That's a good question, I think. Okay, I'm gonna continue here. I'm just gonna take this one and ask Claude, like extract where exactly they. Let's see what this paper claims. The original one. Extract where exactly do they prove that? Hopefully they are not using different notation. I feel like they do. The claim you're asking is established across multiple results in the paper. Oh my god. Okay. The quartic Melaurinc approximation of word-to-word clause can be rewritten. It's an approximation. Okay. We give a closed form description of representation learning in models trained to minimize the quartic Markov-Ring approximation. Page 20, equations 27. Okay. Proof, page 20. It's also in the appendix. That's funny. Okay. Oh. 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 Setting the contrastive. Okay, let me go from scratch. Under setting 3, under equation 3. Proof. Okay. Define M as this. Rewriting equation 3. Equation 3 is this. The quartic approximation. They are using some quartic approximation. Are they using Taylor? Oh. Oh, they are doing Taylor approximation. Sure.
Yeah, I saw something like that from Claude too.
So they take the word-to-vec clause, they take Taylor approximation, they rewrite Taylor approximation. Equation 3. So this is the Taylor approximation then, I think. Rather than approximate the minimizer of the, we obtain the exact minimizer of a Taylor approximation. What do you mean? Rather than approximate the minimizer of loss, we obtain the exact minimizer of a Taylor approximation. Oh, so they take the Taylor approximation and then obtain the exact minimizer for that Taylor
Hello, I'm back.
approximation. Hello.
You guys
Okay,
are
so-
still looking at the proof and the theorems for the transformations and everything?
Yes. Here's the Taylor
what-
approximation.
What do you learn?
Then they rewrite it. Suddenly M star pops out of nowhere. What the fuck? Word2vec. Oh, because Word2vec has in it. Okay, that's actually not that surprising result. Wait. How is it not that surprising result? I need to sort it in my head now. Hold up.
Mm.
Hold up. Wait, what? Why am I
What are you
listening
doing,
to
Barney?
Justin Bieber, baby?
Are you just struggling on that paper?
I'm now having a mind blown moment. Wait a moment. The Word2vec in its loss function has Pij. Is there a there is no such, but it is not true that if you have something in the loss function that the model will exactly minimize it. That's not true in general.
Yes, but I guess
isn't it
if
isn't it going to like the like lowering the derivative,
Loss
like it
function.
tries to lower the loss in any way. So it
Yes,
doesn't
Yeah, but
necessarily
like
mean
no,
it
but
doesn't
yeah,
minimize every variable. It can minimize certain variables. Like it can minimize one variable and maximize another, maybe.
this paper is assuming that with the word-to-vec loss function. Okay, so that I guess that goes into some other paper that would have to say no. The point is that if you put something in the loss function, it doesn't mean that the model will exactly learn that.
okay, but you can. I think it's not. The model will get low loss is not that bad an assumption. As long as you treat it as an assumption. Like if you are saying it's mathematically true that this will hit the but your models are probably going word to word gets low loss, so it probably represents this thing. Or if it gets very low loss, it has to represent this thing to get that much low loss. You can probably say something like that, right?
This is so fucking interesting. Oh, okay.
What?
This is still in the whole space of why does gradient descent actually follow the loss in wait, you wanna minimize that, right? I mean, sure, but then the whole paper is like, of course it will minimize loss. You can derive the shapes from the loss.
You can derive
I
the
wanna see
shape
how they derive the
from
shapes.
from word co-currency is more or less what the other thing paper can say, and that's still interesting. But how
But
do you
this
derive
this whole thing, the whole paper, like they have Gemma examples there. There is no word co-occurrence in the loss function when you train Gemma.
Yeah, but well, Gemma has next token prediction, so it's trained on co-currency of a word with the whole context, which you can get lower loss by approximating bigrams, and then you get better loss by approximating more complicated stuff. But it's definitely like something where it's not unrelated. Definitely, like the model learns
Okay, that makes sense. Yeah.
structure on the data, and word co-currency is part of the structure it learns from. The thing is, of course, it learns from more complicated. You can't learn the counting task example from word co-currencies. It's other kinds of structure, but maybe there is. You can make some more generalized point about symmetries on the data and how that leads to symmetries on the representations. But yeah, I'm not sure I understand the thing enough to get how much this is moving towards that versus just a very trivial example. The result that is will require a much more complicated thing for actual LLMs in a way that this doesn't help much for doing the complicated thing. Yeah.
This is a good point, though. You could say that transformers are doing more general way version of this. Yeah. Here they just look at the occurrences.
Like you could imagine a paper that's like, okay, we assume that the transformers are going to perfectly approximate the the infinite well, I mean unitarianization for that, but perfect text prediction or something like that, which will be like the co-occurrences of text for n elements or whatever. And you can maybe have some things from that thing, because the transformers are not going to get anything closer to the perfect text prediction thing, because that's like it will be like some simulation, perfect simulation of the universe or something.
Yeah, basically. Yeah.
But
Hmm.
or if represented as some kind of lookup table, look some galaxy-sized thing.
A large lookup table for some galaxy-sized thing. Yes.
Yeah, like I mean, if you take a big table with, if you have this combination, all possible combination for words, this is the probability of the next one. I think that's
As
this is the
IC, essentially.
Yeah, no, IC is more efficient.
Or, yeah,
more efficient
it's
than
a
that because it's
subset.
taking programs that generate that. This actually
Oh,
IC
yeah, that's
wouldn't
true.
like that. We'll have this as an hypothesis, but we'll really not like it because it has
Oh,
a
yeah,
very long length.
Correct. Yeah. It takes the lowest logum of complexity program, I think.
Yeah.
I see.
Yeah, it takes the long of it doesn't take the lowest probability. It just gives them a probability based on a prior based on the length of the program.
Okay.
There's a prior that has a nice property like it gets divided by 2 for every bit, so it's a big sequence that adds up to 1 on the infinite limit. But don't worry about that. Go back to the current thing.
I'm gonna see it through here. Considering all possible computable explanations with prior probabilities weighted by their algorithmic simplicities and updating their probabilities based on how well they match the observation. Oh yeah. So you want a simplicity and you want matching observation. I've seen so many formalisms that are like combining program length with like accuracy predictions. That's so common in theory. Okay, whatever. So is large for words that occur for small words that doesn't. Is small lines these words that are in a break of. Why? Like, yeah, I guess. Okay. Now it makes more sense. Like, you in here, you just derive the shapes from the loss of the well, a slight approximation of the loss of the word to vec, basically. So it's not that mysterious suddenly. Wait, it's still mysterious. Why would gradient descent prefer this?
Because it has lower loss.
Yeah, just more compute and it will have lower loss for everything with sufficiently general architecture. Okay.
Oh, yes, you have this. Okay, so why I'm confused. So let's say you have some vectors. Some vectors for the. I guess this is from the word to vec. The word to vec just has to have. So it's. What is the thing on the loss of the work well? Let's say I have a vector for some months and a vector for some other months. What is the loss, that loss term doing?
Yes, wait, let me see you the first term. Why is the first term not in Claude explanation? Oh yeah, the coefficients in the paper versions are just reweighting factors that account for engineering tricks like downweighting very frequent words that don't carry much semantic. Okay, yeah, like literally, it's literally what this paper is analyzing. Like, probability of two words together divided by probability of one word and times probability of
Okay,
second
but
word.
you say the loss is just the co-occurrency of the words, right?
Basically, you could say that.
Okay, but
yeah.
it's not. It doesn't. But why the co-occurrency of the words leads you to some shape in the embeddings? Like, why those things that occur together more often will be closer on the embeddings are more separated on the embeddings than things that occur together less often?
You get the if you plot the co-occurrency, you then you get the matrices
Yeah.
where you see the periodic structures. And if you take the PCAs or all Fourier transforms and so on, you recover
What do you
all the
take
different
from the?
shapes.
How do you get from this matrix to the shapes?
I think here they take PCAs. Let me see exactly what they do in this paper. They do eigen decomposition. Okay. Factorization. Yeah, they do. I decompose the seasons, and so you get the Fourier like thing. That's the matrix, and then you do the PCA on this high dimensional space, and because they are so.
Why? Okay, wait.
Let me go through the
Why-
example in more detail. I
Why
want to
do
do
the
that
model? What does the model represent the matrix?
because that's literally the loss.
No,
Structure
but
of the loss.
isn't the loss? Okay, the loss is co-occurrency, and then it makes sense for it to represent that. So it.
If you rewrite the approximation of
Okay.
of the Taylor approximation of the Vortuvec loss, you get the loss that we were like.
Okay.
How was that proved?
So
That like the model must go to the co-occurrence matrix. So in the limit, you get
doesn't this all is just conversion the same explanation as the Quest-Gourmet thing? As in the reason
what?
so the counting task paper, right?
Yes.
So the reason there is a circle is because the model is trying to represent the months in a way where months that are closer to each other are close, and months that are not close are not close, and the last month is connected to the first month, and that makes a circle.
Yeah.
What does the paper we read today as that's not just that? Like, I guess it said something about the other shapes with those curves. What do you learn about the shape of the curves?
I
That's
think
interesting and new.
I think they frame everything in such a math language that you can basically generalize it. So they use translational symmetry, which you can which itself is very general, and you can find arbitrary translation symmetries in the data, and you could possibly maybe generalize it to more symmetries than just that.
Yeah. I feel like there is another way in the other paper. The counting task explanation was more general than this one in a different way, although less general. Maybe you could combine both in some ways. It's because that one was
Right.
talking about in general about representing the model, trying to represent things in some space that are some shape that have this structure, right? Where some things are connected and you want some things to be closer to each other and more separate to each other for other reasons that rather than co-occurrency.
Yeah.
I feel like maybe
You mean the
here
previous
there's a
group theory paper?
co-occurrency matrix. I feel like can't you derive the same kind of results from any matrix? You have some matrix of how two variables could need to be related in some model, and you get some shape of how that has to look like in the embeddings if you want to represent the relationship as being things that are more related on the matrix being closer and things that are less related being separate?
Like one thing I'm still confused here is that this is the underlying assumption here is that the model goes to the loss in the limit.
I mean, but
And if
we can take it for the realistic cases as if the model, since the model gets low loss, you are going to see some symmetries represented like this, right? That doesn't tell you for any symmetry is going to be represented, but I do think anything that's not like a super complicated thing that's basically rerunning gradient descent doesn't tell you, or like making some theoretical thing about gradient descent and exactly the optimizer and the actual transformer architecture and all of the details. Oh, you're also layer norm using your norm this way and all that. It feels like it will be super complicated to predict in practice this kind of thing.
I mean,
but
the line breaking paper, you know, they had the physics simulation.
yeah, I mean, I'm saying this paper seems like it's a massive way of saying the same thing as the physics simulation says.
It is. I don't think it's the same thing since it doesn't look at the training dynamics. It just looks at assuming the model converges to the loss.
But I feel like the same thing as this model is talking about the thing this model converges to, and you get these shapes, and this paper is talking about word-to-vec, but it's talking about word-to-vec, but you probably can make a more general version if you think about the same physics as this they are talking about the model, where the model is trying to put some things closer to each other and some things separate to each other, and the paper is talking about co-currency on the work-to-web case, but it could be, abstract numbers, some relationship within abstract, like the abstract concept of numbers or something, instead of
like the issue. Yeah, like I don't think you can. Like the issue. The issue is this paper is you have to have the internal loss. You have to derive it from the loss, basically.
No, but on the not on this the previous paper, the one that we read today at the start, right?
Yeah, today in this paper, it's all derived from the loss of the.
But
isn't
it derived from the matrix? Like they are just assuming the matrix, right?
Yeah, you can rewrite the loss.
Learns the matrix. But I'm saying that can't you do the same derive the same kind of shape from other matrix, and the assumption that the matrix represent how close together things are?
Maybe if you, maybe. Maybe if you would take the next token prediction space, which is impossible and interactable. Well, in modular addition, if you just do modular addition,
okay,
maybe if you just
let me take the example. The words the transformer circuit thing. Well, the context task thing. In the context task, we have length of a sentence, right?
You would have.
Sorry, imagine you have the representation from different for the length of different sentences, right? Imagine we put them on a table and we make some matrix where lengths that are more similar are together and lengths that are less similar are separated, right?
Yes.
Can't you use the same kind of math they use from the other matrix, the co-occurrence matrix, that you'll get these shapes? to get that you'll get the same shapes from the thing. And also this math is just equivalent to the same logic as the physics simulator there.
Maybe if you
Which is basically
take-
if the
I mean,
real representation is a circle, and if you try to compress it, you get this weird shapes because they are trying to maximize the distance.
you'd have to somehow do it from how do you call it, from the cross entropy loss.
No, but I don't think so. Because so let me explain. Maybe I'm explaining correctly. I'm wrong that this paper, the role of the laws is just saying that that they are not talking about the laws, right? That they talk about the other paper, and this paper they just take from the other paper as an assumption that the word to back represents M the M matrix, right?
From this
Not the
paper, yeah,
one you are
they
looking
take
at,
that.
the other one, like the first one that we read today.
Yeah, they take this assumption that Word2Vec
Yeah.
must in the limit be the same as the
Okay.
N1.
But can't you just show that if you think that a transformer is going to represent some matrix, it's going to have a shape like that? Some matrix where the represent some
like
matrix,
you would,
where the terms of the matrix represent how close different points are on the
like
representation.
you would have to have the like you would basically have to take all the different probabilities in the cross entropy loss, like take all the different probabilities and just graph them. I think
But
you
they
might.
don't have. I don't mean. I don't. No. I don't. You don't need probabilities. Like, imagine that you replace the M matrix for a different matrix that has numbers that don't represent probabilities, but represent some closeness in embedding space that the model wants. Don't you just get the same shapes? I should explain it correctly.
Like the matrix in this context,
The matrix
has,
is just some numbers, right? The matrix is just some numbers.
yes, but in this
Also,
context, this concrete matrix has the is the conditional probability of the two variables minus the. In this context,
Yeah,
it's
but-
just comparing two things, yeah. And
yeah,
then you
but
take the dot
I'm
product,
saying
cross product.
what property does that matrix need to have? Like, imagine that it's not probabilities. Imagine that it's some random numbers. You have different matrices, right? Matrices are just a list of numbers. Imagine you have different matrices. What matrices, like, what's the property that matrices have that makes these shapes?
Oh, I think I'm seeing what you're trying to ask.
Like,
You
how
have
they are
to-
related to the...
They
to
define
the-
it here, actually. I think they use concrete terminology. Here, circulant matrix. Yes, circulant matrix will produce circles, and Toeplic matrix will produce
okay.
lines.
But okay, so you have let's say we have a circular matrix, but the matrix is
In this context, it's like the dot product of like the associations, like as in
what does the word to back is trying to do to minimize the? So is the word to back trying to make things that are closer, vectors that are closer, that have higher concurrency to be closer on the embedding space?
Yes.
Okay,
The
but
closer they are
doesn't this
together.
generalize to if you have a matrix of how close. If you have a circulant matrix that represents how close 2 points are in the embedding space, you are going to make a circle.
Yes.
Okay.
But this whole paper is based on the assumption that you're starting with the Bortovec loss, which is
Okay,
explicitly.
but I think that the Word2Vec thing basically can't really generalize to the all of the transformer cases, and the transformer
Yes.
cases have the same shapes because these same shapes are come from a more general math thing, that is, if you have some structure on the data and you have some points that have to be closer and so on, they make these shapes.
Yes, but I think it doesn't work in general, because you can have these kinds of symmetries in the training data, and the model doesn't have to learn it.
Yeah, but I'm
But it
saying
often
if
does.
the model does represent as the relationship on the embeddings as points being closer to each other, they'll have to make those shapes necessarily. Like, they have to make a circle,
Yes.
for example.
Yes, I
If you
think
have
so, because
something like mouth, it necessarily makes a circle.
because you basically just get that by taking this matrix and doing dimensional reduction, and that's the dimensional reduction.
And
If you do
but the thing is, this is
the
thing.
PCA on this.
Yeah, but
This is the circle.
also the argument that is making they're using here. They are talking about isn't this also the same point? Now that I see this paper, they actually were saying the same thing here, right? On this figure which you are looking at right now.
Yeah, they have a different physics model though, and I don't think
they're talking about they're talking about the similarity matrix and how it makes different shapes, right? And the other paper is thinking about the pairwise.
Yeah, like literally they do actually when I think about it. Here you see it directly. Here's your toy model. Here's how the GPT-2 solve. Literally they doing the same thing using different math.
Yeah.
What are
They
they doing the
actually
same thing
use
for?
proper math. Like here, they use all the terms, which makes me happy. They say, "Oh, circular matrix, etc., etc., etc." But they
but
just
I feel like
use
they are
word to vec
making
only.
I feel like they are making it too narrow by talking about the word to vec thing. And they are making a weird way that makes it seem to imply that and they also think they are confused, because I think they talk about in the confusion. I mean on the new paper, not on the anthropic one. The anthropic one is correct. the new paper feel like they are confused in thinking that the transformer shapes must be related to pairwise similarity, right? But I think it's a more general thing that out similarity, it works with any similarity. It doesn't have to be a two-word relationship. Right?
Oh, I think I see what you mean now. Yeah.
For example, on
Yeah. But they say that in the paper. Actually, I think they say arbitrary. They have a general framework for that. That's the convolution. Convolution, not this paper. The other one. They use the convolution kernel, I think. Is co-occurrence convolution kernel distance. Like here, you can give arbitrary distance. You can define arbitrary distance. So this is a like
but I
in
feel like
math.
that you
There's
could
anything
make
where you can measure
a
distance.
nicer math paper where this less complicated even, that talks about models having these structures because they represent similarity of two concepts, that they don't have to be words that have some probability together, right?
Yeah, cosine similarity.
Yeah.
Like also here they use a different way to create different math to do the simulation. And they do, and here it's also, they don't do any analytical derivation. They just do
And
numerical simulation, I think.
Let's say about the modular addition example, right? In modular addition, in the Grokking paper, the model doesn't learn the structure because co-occurrences between the two numbers, probably. I mean, there's maybe co-occurrences between the two numbers in additions, but I don't think it's because of, it learns it because representing the numbers in a way that has that similarity gets you the right answer on the third number, which is the output, right?
That's one way to see. Yeah,
So
that's one way to
it's
see it.
kind of a different thing that
Yeah, that's
has
yeah,
the
yeah,
same
yeah.
shape for the same math for because it's also a different kernel, but the reason is different than in the word-to-way case, because in the word-to-way case you get the similarity kernel because of the loss, and here you get the same thing for a different reason. I feel like it will be more applicable to transformers to talk more about the general shapes. Also, this means that we could get some idea of some symmetry on some kind of data that has some symmetry, right? And we well, remember that you are still being recorded right now, but your screen
That's
about
good,
that.
I think. Yes.
But we could take a model. So we could take some kind of simple thing or simple task or simple thing that has some nice symmetry or relationship with where to solve it. It seems like something like months, but something else that is not months. That seems like it has some periodic structure or something, or some things are closer to each other than some other things, and predict that it will have some shape in the embeddings or the hidden states of the model, and see that shape later.
Here they, from the months, they do derive the shape. And the months are
Like
co-occurrent.
in fact, you should think like, okay, days, years also there. What other things like that are there? I guess something can be anything that's a count. You should expect all kinds of counting things to be same kind of curve, right? And you can figure out if it's a kind of curve potential circle or not.
I think in general anything that's equivalent to a circular group, basically.
Yeah.
Or like, I guess that well,
It's
maybe
related
more
to the
generally.
universality paper.
Yeah, actually, yeah, a lot.
Everything is connected. Getting paper psychosis.
I think, but the issue is still not every group is learned by transformers properly.
Yeah.
We could even see that on the paper last week. If you had a group, it didn't learn all the axioms. I think the associativity wasn't learned, even if it was obvious in the string data. So
yeah.
Also, like,
maybe a bigger model will learn it, or they need to fiddle more with their parameters and all that.
Yeah, okay, yeah, just bitter lesson more, yeah. And
I didn't ask that much about that that time. Maybe I should have.
Yeah. Also, by the way, there's this other paper which I shared, which I really wanna read, which is like trying to mathematize the modular addition task, the Grokking task.
Oh yeah, I saw it that you link it. Yeah, like it's more the modular edition paper, but even more math.
Yes.
But yeah, I won't put that one for next week because I feel like people need
Break.
less math paper for next week. We can do it after that though.
Yeah. Our work provides a full mechanistic interpretation and theoretical explanation of its training dynamics.
No, yeah, it would be that my main question about that paper is how novel compared to the thing that we already have on the Niels paper is it? You know?
Yeah. Phase symmetry and frequency diversification. Interesting. I think that's kind of new.
And yeah. Anyway, do I stop the recording and we leave it now? Because
I think I still want to finish this example real quick. I haven't gone through the whole example.
Okay, finish doing that then, and then we'll stop the recording before it.
Yes.
I mean, it already went 4 hours, but
Yes.
we're-
So the of the equals the eigenvector. Okay, now I see why. I'm in my mind. It's like no, this isn't general because they never fully follow the laws. Even like if you have physics-inspired neural networks where you put conservation of energy in the loss function, they still don't do it fully, and you have to do more tricks. Also, conservation of energy is a symmetry, so assuming transformers line or symmetries, you would just need a transformer, and you wouldn't need any physics-inspired. I mean, yeah, I think it's called physics-inspired, like Lagrangian neural networks, for instance.
I mean, maybe you
okay,
don't.
whatever. Okay. Yeah, I guess we were just not creative enough, maybe. The symmetric version fixes it, so it also has, yeah, I guess that flows from how the singular value decomposition works. Okay. This means that the PCA geometry of the embeddings reflect the matrix absolute value of, yeah. The PCA just takes the eigenvalues, right? I think, do I remember correctly? Let me just quickly check. I think the middle matrix. Wait. Largest variation. Yes. Which are, yeah. Yeah, well, it just computes the highest variance. What is the thing that computes? Yeah, eigen decomposition is the thing that computes eigen decomposition. Oh yeah, that's what I meant actually. Instead, and PCA just finds the explaining the highest variance. For some reason, I merged it in my mind because one is SVD, another is CVD. Okay. No, SVD is also another different thing. It's diagonal with non-negative entries, singular values. My god, I forgot singular values. It is single values are derived from eigenvalues. Wait, how much? Hey, there's also the rotations in the matrices, right? Yeah, right. I remember. SVD is just In SVD, they're all real and negative. Okay, sure. So finally, an example. So you take seasons M, which creates this 4-to-4 matrix, which is approximately circulant with those values along its first row. For circulant matrices, the eigenvectors are always discrete Fourier basis. And I want the original paper. I think is this one. Yeah. Eigenvector constant mode. What do you mean by constant mode? Oh, it's just a constant. Just one. So, okay. Why is there this eigenvector with discrete Fourier basis? I forgot. The different frequencies. So this is another frequency. Same eigenvalue. Okay, right. So this is just constant. This is high frequency. I mean lower frequency, and this is high frequency. Removing the constant mode. Wait, let me Neil Nanda-Drucking. I wanna see the graph. Frequency 0. Oh, right, okay. If you have 0 frequency, you just have constant in the Fourier decomposition, right? And I have another discrete one, discrete Fourier transform. I just wanna see the graph. Well, I guess so. I mean, you can start, but you don't have to. Why are you removing the constant mode? You want the eigenvalues, no? Okay. Okay, the Fourier coefficients are real and they decay rapidly with k. The eigenvector associated is the constant mu, representing the global season mean. The global season mean? Huh. Where am I? I'm in here. Okay. I think I don't see that from the example. Every board has the same value in this direction. Oh, right, okay. Sure. Yeah, like if it's the same vector for every word, that makes sense to just, to just restrict it. All right. Sure. For spring, you have Where did you get this? Yeah, like it's so confusing here that like if you start the paper, they instantly jump into this. Obviously, the layered embeddings are this. But in order to understand this, you have to look at the other paper. Well, yeah, they actually cite it here, so yeah, it makes sense, I guess. So this is in equation 4 in proposition 1. Oh, okay. S is for seasons, so blah blah. The eigenvalue L. So we have different eigenvalues for the different directions. And x1 is for spring. Spring is at angle 0. Yeah, this is another thing. When you try to make cloth to plug stuff in, you should mostly ignore the concrete numbers because it just makes it wrong often. But like for conceptual plugging in, it makes good enough sense, I think. By the way, if you said something, you're muted, but I'm not sure if you are saying something.
I don't know. I was not saying much, but maybe I did say something I didn't realize because I was muted.
Yes.
But I don't remember now. It's probably been muted for a while, and maybe I said something else important, but I don't even remember now.
Okay.
To be fair, at some point I just kind of just not. I kind of just tired and not even thinking about this anymore.
Okay. Yeah. I just wanna go through the example. I think I'm starting to understand proposition 1 finally. Okay. Wait, I need to go back.
Yeah,
Where
maybe
was
for
it?
these papers, maybe it would be better if we did this before the reading group or something.
Yeah,
I don't
that's another
know. At the
option.
same time, it's hard to motivate yourself to do that if
Yeah,
it's not.
basically. It's better to do it with someone together. Yeah. I can read papers much better when reading with someone. So this is the proposition 1, all right.
We know we just need cloth to be on Discord for you to read papers with cloth.
Yeah, but that would be hard to double check real time if he was talking and to copy his equations from his words. Would need to have real time transcription as well. For summer it has this, for winter. Yeah, like you just take the Fourier. The proposition 1 is how you get the shapes. So wait, let me see how it's in the paper. Let S correspond to a periodic semantic lattice. So you first have to assume. They use the word lattice. Do they define latent semantic lattice? Let me see if they defined that before. No. This is a word they didn't define. Does it have a formal? Oh, there's more. Lattice is a thinking group theory. Do they mean that? No, I don't think they do. Because I think they mean this lattice actually. I mean, set L to binary operations. Minus plus, minus plus. Sure. Let's ask what actually they define it. But that doesn't seem to be that important. Under periodic BC, what is BC? Boundary conditions, okay. Periodic boundary condition, the corresponding submatrix. Submatrix. Oh yeah, that's the. Like I don't know how you would like understand this without just going through all the terms before. You just have to know all the terms. Okay. Assume assumption 3.4 holds with kernel C. What was the assumption? That's the translation symmetry. Does C translation symmetry? Okay, whatever. Yeah, I guess he goes into that later then. So translation symmetry: m star ij equals c distant. The concurrence statistic between any two words I and j depends only on the distance between them on the semantic continuum. Not their absolute positions. So m star is the matrix, and j is always equal to f. Wait, assumption 3.1. FC distant. Sure, what is the F? Convolution kernel C is just simply representation of C star.
Also, I think Claude got the thing I was talking about by just me copy pasting linking the anthropic paper and asking it how it's related.
Oh, okay. You mean the first or the second thing that you sent?
No, this is a new one. I can send it to. But continue with your thing. Don't worry.
Okay.
I'll send it you later. But probably better if I don't. If you finish before I distract you with a new thing.
Okay. Oh, I see. Claude does from scratch explaining, and I'm surprised Claude does from scratch explaining and doesn't jump. That's good. It's getting really good at this explaining. That's good. Like when I do this kind of pipeline. Is it the pipeline method of explaining math for a long time, and I can see how it's getting better and better.
Also, I feel like Claude is better at some kind than almost anyone at some kind of like reading trying to understand what the other person means thing, where I feel like I have much less trouble explaining things to Claude, explaining things to you, or to even though Claude makes a lot more mistakes than do you, and once you understand it, you reason better about the thing. But the part of explaining it feels like Claude is better at I don't know, some kind of reading comprehension thing. To be fair, maybe you will be better if I had to write the thing and having to me badly explaining of voice. It's maybe harder to understand.
I think this is true for yeah. Also from my experience, probably. I guess depends on what exactly. Just you can follow extremely specific instructions, and many people just cannot. For instance, I guess that's one aspect. For instance, yeah.
Also, I guess Claude also generally knows about everything, and so
yeah. That's another aspect. Yeah.
And also another aspect is that I can just. I try to when I want to explain a thing to you, I need to explain what thing on the paper I mean or whatever, and Claude I can just give it the entire paper and have it read the entire thing. I will you to take like an hour of reading that.
Yeah. Continue learning partially. Makes me wonder how what all sorts of superhuman qualities we will see soon that are that human brain is just limited by. Yeah, that we already see some, I think. C distance. But I think I also generally takes slightly longer to process, but I don't know. Depends, I guess. Distance ij xi. Like I have to, in order for me to like grok it, I just have to construct some kind of structure in my mind that's just coherent.
Yeah, I mean, to be fair, at the same time, Claude will try too early. Claude is faster, but it's faster wrong sometimes.
Yeah. Do you know the new? Do you know the new? I think it's called Jimmy or something LLM thing. Like someone made hardware where they literally ingrained Llama 8B weights, so it's like like I don't know 10,000 tokens per second or something like that.
Oh yeah, I saw that.
It's insane. Yeah, like Oh wow! This is the first one of the first thing LMs will get superhuman at. Imagine Claude Opus level intelligence at this like speed. Like what the fuck?
Yeah, that's just the kind of thing. And another reason I don't think it makes sense. People's take. I feel like a common take that people that don't know much about machine learning have is that if AI, and did you see this with DeepSeek? And also, I saw a YouTuber say something recently, like that if AI became a lot more cheap to run, data centers will stop being useful. The giant data centers, the AI industry will blow up or something because they don't need, in quotes, giant data centers. I think that makes no sense because you can trade off more compute for more better lesson and more better models.
yeah,
And
right.
but even in the world that those people are probably imagining where the models just don't keep getting better because I don't know, they don't know about the scaling laws or whatever. That wouldn't happen because then the AI model companies will just be serving you products where they have cloth running at those speeds or giving you a swarm of thousands of cloths for one query, right?
Yeah. I feel like that's some kind of cognitive bias. Like people used to say in the history that like computers will
Also, I think
will
the people
yeah.
make in general this kind of mistake in economics in general. And I think that has a name in economics that's probably related. I don't remember. I remember my
Hmm.
brother who studied economics talk about this and things about like
The-
how people expect more, I don't know, a bigger, like you add more less traffic when you are more roads and there's more traffic because people use those modes, but it's still better because people are getting more use from the roads. I don't know, it feels like it's related to that. I don't remember the name on that.
feel like it's an instance of status quo bias where the incorrect assumption is that the current production will never grow. So if you increase the supply, you will never get bigger demand in a way. You oversaturate the demand.
Oh,
I think
it's
it's
yeah.
mistaken the
Actually,
direction.
the thing I'm talking about is Jevons paradox. Actually, this is exactly this thing. Jevons paradox. Yeah, that's the name of the thing. Which is technology can increase the efficiency of the recurse layer to arise the follow the total consumption of the resource. I
Increase in
present it
efficiency
on.
in resource use will generate an increase in resource consumption rather than increase. Yeah, that
Yeah.
makes sense to me. Yeah,
I think
I think that's
people.
correct.
I think this just happens in general, and the paradox is that people have the wrong idea that this won't happen, and they are consistently confused when it consistently happens. That increases the efficiency,
Yeah.
makes things consume more of the thing.
I think it's status quo bias. Like in instance of that, like what's happening cognitively. That's also why people cannot grasp exponentials. I think, like nothing ever
I mean,
happens by it,
also
basically.
empirically, models became much cheaper. Like you see,
Oh yeah,
yeah, like this already happened, and the thing that people expected to happen didn't happen. Like GPT-2 is they made even bigger the centers. GPT-2 to cost like $40,000 to train, and now Caparti train Nano GPT with similar performance for like $20.
yeah. I've seen that. Yeah.
And this didn't make AI thousands of times less money. Kind of the opposite.
And if you wouldn't use Python, I think, and so on, like you could get even lower and so on. Yeah.
Yeah.
I think people were
I-
optimized it to oblivion.
He also
We were at the
now that
beginning.
he did like I don't know if you saw, but he was doing a thing that this was not optimized, but was I don't remember the name. It was micro GPT or something like that, or nano GPT. No, the nano GPT is the main one.
You mean NanoChat?
The thing that's very very small, like no Python library. It's just
Oh
the
yeah, I know
GPT-2,
what you
the
mean.
simplest. Yeah, I don't remember the name, but it's yeah.
I also don't know the name, but yeah, I see what Pico GPT maybe.
But yeah,
Maybe.
probably
Pico.
yeah, because the Nano GPT is just the normal, the efficient version.
Yeah.
I think he made a new one that is just him trying to, instead of being the most efficient possible, using the less lines of code possible and using only Python without any libraries.
Next one will be Utah GPT.
I mean,
Which is
that
even
one
lower.
doesn't do it. Basically doesn't generate any. It's really really bad, but it does
Yeah,
work, and it is the
it's not
GPT
using
architecture.
optimization. Yeah. Like PyTorch is optimized to oblivion. And
You could probably get GPT level like GPT whatever level performance by training it on a galaxy size computer.
Yeah.
Maybe not. Maybe it breaks for some reason with you don't change the code because some the thing like you run out of some maximum float size or something. But yeah. Anyway, sorry, I got distracted. You did it. We're still recording and you didn't finish figuring that out. So continue
Yes,
with
let's
that.
finish.
Sorry.
Okay, concurrent status between two words only on the distance, not the absolute. So this is the distance thing. But what is the J? What is the C? C is the kernel, no? It's some well-behaved functions. No, it's a kernel. I wanna see example of that. Maybe explained later. But only on the distance between them. Yeah. Some function C called concurrence converge such that PJ. Oh, okay, I see. So that's the kernel. Is the probability. So the probability of them occurring together is them separate times you take the distance and do the C thing. Some function. Okay. Such the normalization of equation 1. I think it's the equation 1, right? My J. You define it as this? FCJ? Okay. Where F1, Fy, you do this. Okay, whatever. I still don't see the convolution kernel example. Okay, whatever. I'm getting to the translation symmetry slowly. Let's see. Simply a reparameterization of C. Sure. They use the kernels later, okay. Sure. Each word I gets according xy on the semantic coding normalized on the interval -1, 1. Example A seasons with this periodic. X and I. Two and -1 for okay. Matrix M star restricted to S has a very special structure. Periodic boundary cycle matrix. Claude is like, this is why Fourier decomposition appears. It's not imposed by the model. It's forced by the symmetry of the data. It's not why. It's like, and also it's not forced, but it's forced. Okay, whatever. No, in this context, it's forced by literally the loss function being equivalent. It's not in the data. Okay, whatever. Let's continue. So, Fourier embedding geometry proposition 1. Oh, okay, here goes in the proposition 1, sure. Under translation symmetry assumption. Any two words in S. In S. What again is the S set? S might be 12 months. Okay. Assume this. Sure. Flow that the co-occurrence matrix inherits. Huh?
Burni, is
It
this
follows.
true? Grok.
You're sending me in PM? Or
Yeah.
okay. Yeah, I'm just trying to reverse engineer the proposition 1 now.
Mhm.
If a matrix has translation symmetry, its eigenvectors are Fourier modes.
Is that true in general?
I'm not sure if in general, because I have to yet look at the example of where it's true for the line, for example.
Okay, continue.
The co-occurrence matrix is just the specific matrix they plug in. Maybe. Let's see. Under the co-occurrence matrix defined in equation 1. They define the co-occurrence matrix as literally the loss of the... I'm noticing just now here. They just literally define it as the Word2Vec loss. I think. Okay. Sure. If we're optimizing for Word2Vec, then we will get Word2Vec. I'm not surprised. Okay, whatever. So, and by the eigen decomposition, you get this. Yeah. Yeah, I'm a bit confused here. What do you mean inherits the translation symmetry? I want proof.
Well, I mean, the translation symmetry, like it says that there's a translation symmetry. This is the assumption, right? It's just inherit. So never mind.
Yes. Like this is like proof is an exercise for the reader level stuff. I feel like.
Yeah, I feel like in any case, the interesting result it will be more on the direction of if you have a symmetry, this happens. But I don't know.
Yeah. Need algebraic cancellation, so it was an exercise to the reader. When you substitute the assumption to the formula, the assumption says this. Pij is this. Sure, you just factor out the associativeness using the distance. Holy shit. Okay, that's actually pretty general. Now the distance is very general. The matrix M is defined as M star ij. Probability of those. Oh. 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 What is happening here? Why did they not prove it? I mean, yeah, but
Why
like
didn't you prove what?
the translation symmetry.
I mean,
Wait. What is
aren't
this
they
last step, though?
assuming the translation symmetry, right? They're like, it's
Wait.
only on the.
You get this. Oh, f is just some. It
Like the symmetry is on the structure of the months, right?
What is this
So-
last step? What is this last step? This seems untrue. You have this function, which is just some well-behaved function. I think well-behaved means something concrete in math. It's pathological. Yeah, smooth continuous, basically. Right. Huh? Huh? F. Oh. Okay, they just pick it like this. Sure. How did you get suddenly distance, though? Is it like proof by it makes sense by intuition? Okay.
The distance is not like
Oh, okay.
It's an
Wait,
assumption,
assumption.
right? About the words. You're saying that months are closer to each other, but doesn't this work with any distance?
Wait. No, this is just plugging in. PIJ. You have PIJ. Wait.
Yeah, but
What?
couldn't you use any other similarity thing, right? That's the thing I was saying the whole time.
I think you can put arbitrary thing in the distance, but now I'm kind of. How inherits?
Should I stop the recording
Explain
because it's been going for like 5 hours and I don't know if it.
I feel like
Hmm?
there's still a lot of math. Wow. I
Yeah,
want to
well,
go through all the math. But yeah, up to you.
Yeah,
I might still just try to go through the math.
Yeah, no, we
They're
can continue. It's just I feel like I maybe should still go also leave, but maybe myself. I will still here, but then kind of.
Up to you. Explain all definitions and algebraic manipulations. Finish